Hello there, and welcome to the Cosmographer. The Kuiper Belt is missing about 99.9% of the mass it should have been built from, and after 30 years, nobody can agree on whether it was taken or was never there at all. Number 16 on this list is a plain of frozen nitrogen the size of Texas and Oklahoma combined, with not one impact crater anywhere on it. Number 10 is a ring orbiting more than twice as far out as the distance where rings are supposed to be able to exist. Number 4 is a world whose closest approach to the Sun happens in the 2070s and will not happen again for 11,400 years. And number 3 is a planet several times the mass of Earth that may be orbiting our own Sun right now, unseen by anyone. 20 findings from the largest structure in the solar system, one spacecraft that has ever been there, and no accepted explanation for any of them, counted down from 20 to 1. Get comfortable and settle in. If quietly working through 20 things nobody can explain sounds like a good night to you, a quick like and subscribe helps this channel reach more curious minds like you. Because the entry at number 1 is not the strangest object out there. It is the boundary that everything else is measured against, and it may not be where we put it. Let's begin at number 20. Number 20. The object that spins too fast for its own good. There is a region of the solar system that begins where the planets end, and almost everything in it is a rumor. It starts at the orbit of Neptune, about 30 times further from the Sun than we are, and it extends outward for another billion kilometers or so before the counting stops. It is flattened, like a very wide, very thin disk laid around everything else. It is called the Kuiper Belt, and it is the largest structure in the solar system that we have never properly seen. The idea came before the evidence, twice. In 1943, an Irish astronomer named Kenneth Edgeworth argued that the solar system probably did not simply stop at Neptune, and that a reservoir of small icy bodies ought to lie beyond it. In 1951, Gerard Kuiper made a similar argument independently, and his name is the one that stuck. Neither man lived to see anything confirmed. That took until the 30th of August, 1992, when David Jewitt and his graduate student Jane Liu, working on Mauna Kea with a 2.2-meter telescope, found a faint moving point of light. They had been searching for 5 years and had found nothing. They catalogued it as 1992 QB1 and nicknamed it Smiley. It is now called Albion, and it was the first object anybody had ever confirmed out there. In the 34 years since, the catalogue has grown past 3,000 objects. At least 8 of them are large enough to be called dwarf planets. One spacecraft has ever visited, and it visited exactly twice. Everything smaller than about 10 kilometers across is still completely invisible to us, which means the great majority of the belt's contents have never been observed by anyone and may never be. We are working from a sample, and we do not know how representative the sample is. That is the honest position, and it is why this list exists. 20 things have been found out there that nobody has been able to explain. They are arranged here in a specific order, and the order is not size, and it is not distance, and it is not fame. It is how far outside the object the answer has to come from. At the top of the list, at number 20, the entire mystery fits inside one body 140 kilometers across. By the middle, the answers require a whole population of thousands. Near the bottom, they require a world nobody has ever seen. And at number 1, the leading explanations require something that is not in the solar system at all, and may not have been for 4.5 billion years. We begin with an object that was, for 23 years, nothing but a smudge. On the 12th of May 1994, Michael Irwin and Anna Zitkov were on duty at the Roque de los Muchachos Observatory on the island of La Palma in the Canaries. They recorded a faint moving point in the outer solar system, and it went into the catalogue as 1994 JR1. It sat there for 2 decades with a designation and almost nothing else attached to it. Later it was given a proper name, Arawn, after the ruler of the other world in Welsh mythology. The naming was not arbitrary. Objects that share Pluto's particular orbital arrangement are traditionally given names from underworld traditions, and Arawn shares it exactly. That arrangement is worth understanding, because it is the reason the object survives. Arawn is what astronomers call a Plutino. It orbits the Sun twice for every 3 orbits Neptune completes, locked into a rhythm that repeats indefinitely. Neptune is by far the dominant gravitational influence in that part of the solar system, and anything that crosses its path without a rhythm gets thrown out within a few million years. The resonance is a kind of protection. It ensures that Arawn is never in the wrong place when Neptune comes past. About a quarter of all known Kuiper Belt objects are in this same lock, which makes Pluto's resonance the single most crowded address in the outer solar system. For 23 years, that was essentially the whole file. Arawn was a handful of pixels on a handful of plates. Its orbit was known well enough to say roughly where it would be, and not much better than that. Its size was estimated at around 145 kilometers, which is a guess derived from its brightness and an assumption about how reflective it is. Nobody had any idea what it looked like because nobody could resolve it into anything but a dot. Then a spacecraft went past. New Horizons launched in January 2006, aimed at Pluto, and its route through the belt happened to bring it within reach of Arawn. The first observation came in November 2015, from 280 million kilometers away. The second came in April 2016, from about 111 million kilometers, and at that moment it was the closest any spacecraft had ever come to a Kuiper Belt object other than Pluto itself. It is worth pausing on what that observation actually was. The camera used was LORRI, a telescope with a main mirror 20.5 centimeters across. Even at closest approach, Arawn remained an unresolved point of light. There is no picture of Arawn. There is a series of measurements of how bright a dot was at different moments, and everything we now know about the object was extracted from that. 2 things came out of it. The first was a matter of bookkeeping, and it mattered more than it sounds. The orbit was pinned down about 1,000 times more precisely than any ground-based measurement had managed. That precision killed a suggestion that had been circulating, which was that Arawn might be a quasi-satellite of Pluto, traveling loosely in step with it. It is not. It is an independent body that happens to pass within about 2.5 astronomical units of Pluto and has no relationship with it beyond a shared rhythm. The second result has not been explained, and it is the reason this object opens the list. The brightness rose and fell in a regular cycle, and the cycle told us how fast Arawn turns. It completes a rotation every 5.5 hours. For a body of that size, in that part of the solar system, that is fast. See why it is a problem. You need one piece of physics. Most Kuiper Belt objects are believed to be rubble piles, loose collections of ice and dust held together by their own weak gravity and by nothing else. A rubble pile has a speed limit. Spin it fast enough and material at the equator simply leaves, because the rotation is throwing it outward harder than gravity is pulling it in. That limit depends only on density, not on size. A pebble and a mountain, made of the same loose material, come apart at the same rotation rate. For the low densities typical of icy outer system bodies, somewhere around half the density of water, that limit sits at roughly 4.5 to 5 hours. Orion is turning once every 5.5. It is not over the line. It is close enough to it that the standard picture of what these objects are made of does not comfortably apply. That leaves two possibilities, and no way yet to choose between them. Either Orion is considerably denser than its neighbors, meaning it is far rockier than a Kuiper Belt object at that distance has any business being, which raises the question of where it actually formed. Or it has genuine tensile strength. It is one solid, coherent body rather than a bag of gravel, and it is holding itself together by more than gravity. Both answers are uncomfortable, because both mean our default assumption about small bodies out there is wrong for at least some of them, and we have no way to tell how many. There is one more thing that needs saying about Orion, and it is a correction. A story circulates widely that New Horizons lost all contact during its approach to this object, and that the blackout was somehow deliberate. What actually happened is in the mission logs, and it is a different event entirely. On the 4th of July 2015, 10 days before the Pluto encounter and 9 months before the Orion observations, the spacecraft's main computer went into a protective shutdown. The cause was documented. It was compressing 63 stored images to free up memory at the same moment it was receiving the enormous command sequence for the Pluto flyby, and it was overloaded. Contact was lost for about 80 minutes. The team had the spacecraft fully recovered and back on schedule within 3 days. There is no record of any communications loss at Orion, and the two events are separated by 9 months and several 100 million kilometers. The real strangeness here does not need the embellishment. An object we cannot photograph, whose composition we cannot determine, is spinning near the speed that should take it apart, and the only reason we know is that something flew past and glanced sideways for a few hours. But whatever the answer to Orion turns out to be, it is somewhere inside Orion. The next entry on this list cannot be explained by looking at the object at all. Number 19. The moons that never settled. Pluto has 5 moons. The large one, Charon, was found by James Christie in 1978, and it is enormous relative to the world it orbits, about half Pluto's diameter, which makes the pair less like a planet and a satellite, and more like a double system rotating about a shared point. The other 4 are small. Nix and Hydra were found in 2005 by a Hubble team led by Hal Weaver and Alan Stern. Kerberos followed in 2011 and Styx in 2012. Both turned up during a search that had a very practical purpose. The mission team was looking for hazards along the flight path that New Horizons would take, because at 14 kilometers per second, an undetected ring of debris would have ended the mission. They found no ring. They found 2 more moons instead. In June 2015, weeks before the spacecraft arrived, Mark Showalter and Douglas Hamilton published a result from Hubble that nobody had expected. Nix and Hydra do not rotate in any ordinary sense. They tumble. The distinction matters. A rotating body has a fixed axis. It turns around that axis at a steady rate, and if you know the rate, you can predict where any point on the surface will be at any future moment. That is how a day works. Nix and Hydra have no fixed axis. Their spin axes wander, and the wandering is chaotic in the strict mathematical sense. 2 starting conditions that differ by an imperceptible amount will produce completely different orientations a few years later. Hydra turns roughly once every 10 hours, and Nix roughly once every 44, but those numbers are averages of a motion that never repeats. If you stood on Nix, the sun would not rise and set. It would wander. The North Pole can swing from pointing at the sun to pointing at Pluto within a matter of days. There is no length of day to measure, because the day is not the same twice. No calendar could ever be written there, and no clock built on the local sky would run. The cause is understood in outline. These moons are not orbiting a single point mass. They are orbiting a binary, and the center of mass of Pluto and Charon sits about 960 kilometers above Pluto's surface, out in open space. The gravitational field that the small moons move through is therefore shifting constantly in both strength and direction as the two large bodies swing around each other. On top of that, Nix and Hydra are strongly elongated. Nix is roughly 50 by 35 by 33 kilometers. Hydra is roughly 65 by 45 by 25. An elongated body in a varying gravitational field feels torques that pull on its long axis, and those torques never settle. The moons are being kicked from two directions at once, forever, and they have never had the chance to lock. Chaotic rotation had been predicted long before this. Saturn's moon Hyperion was identified as a tumbler and confirmed by Voyager 2. But Hyperion is a single case, an oddity in an otherwise orderly system. Pluto has at least 2, and probably 4, in one place. What has not been explained is almost everything around the tumbling. Start with brightness. The 4 small moons reflect somewhere between 50 and 80% of the light that falls on them. That is freshwater ice. It is not the dark, reddened, radiation-processed material that coats most surfaces in that part of the solar system, and it should not be there. 4.5 billion years of cosmic rays and ultraviolet light should have darkened those surfaces long ago. Something is keeping them clean, and nobody has identified what. There is no atmosphere to deposit frost, no obvious source of resurfacing material, and no plausible mechanism yet published that keeps a 50-kilometer object bright for the age of the solar system. Then there is the arrangement. All 4 small moons travel on orbits that are nearly circular and nearly in the same plane, and all 4 sit close to simple whole number relationships with Charon's orbital period, roughly 3:1, 4:1, 5:1, and 6:1. Close to, but not exactly on. That near-miss pattern is remarkably difficult to produce. A violent collision, of the sort usually invoked to explain how Pluto got a moon system, should have left the debris on messy, scattered orbits. A gentle capture of passing objects should not have delivered 4 bodies into near resonance with each other. Every published model reproduces part of the arrangement and fails on the rest. There is one further oddity, which is that the 4 moons do not match each other. Kerberos is noticeably darker than the other 3. If all 4 condensed from the same debris after the same event, as the standard picture requires, there is no reason for one of them to be made of different material. Nobody has explained that either. And Nix carries a scar. There is a reddish patch on it roughly 18 kilometers across, almost certainly an impact crater, and the material exposed inside it is redder than the surface around it. On a body 50 kilometers long, an 18-kilometer impact is close to the limit of what the object could have survived at all. Whatever hit Nix very nearly ended it, and the moon is still tumbling with the mark on its side. There is a final contrast worth drawing before we move on. While the 4 small moons cannot settle into any stable rotation at all, the 2 large bodies at the center of the system have settled completely. Pluto and Charon are mutually tidally locked. Each permanently shows the same face to the other, so that from one hemisphere of Pluto, Charon hangs in a fixed position in the sky and never moves, and from the other hemisphere it is never visible at all. That is the only known case in the solar system of 2 large bodies holding each other in a mutual lock. So within a single system, a few thousand kilometers apart, we have the most stable rotational arrangement we know of, and the least stable one, produced by the same physics, acting on bodies of different shapes and sizes. Everything on this entry comes back to the same point. Nix and Hydra are strange not because of what they are, but because of where they are. Take either of them, put it anywhere else in the solar system, and it becomes an unremarkable lump of ice, with a steady day. It is the presence of the binary underneath that scrambles them, and no amount of examining the moons themselves would ever have revealed why. The next entry works the same way, only more directly. It is a world that has been marked, permanently and visibly, by the world beside it. Number 18. The Moon, painted by its planet. When the first high-resolution images of Charon came back in July 2015, the feature everyone noticed was not a mountain or a canyon. It was a color. Charon's North Pole is covered by a broad dark red stain, roughly 475 kilometers across, sitting like a cap over the top of an otherwise grey and icy world. The mission team informally named it Mordor Macula. Nothing else on Charon looks like it. Nothing else in the solar system looks quite like it either. The explanation published by Will Grundy and his colleagues in September 2016 is the only serious one anyone has produced, and it is stranger than the feature. Pluto's atmosphere leaks. Methane escapes continuously from the top of it, drifting away into space, and a fraction of that escaping gas comes under Charon's gravitational influence and is captured. Now consider what Charon's North Pole is like. Because of the way the system is tilted, that pole spends roughly a century in unbroken darkness at a stretch. During that century, it cools to something in the neighborhood of 15 Kelvin. That is cold enough for methane to freeze solid the instant it arrives. The pole becomes a trap. Over the course of a long winter, it accumulates a thin frost made of Pluto's exhaled air. Then the sun comes back. Galaxies will continue to drift. Ultraviolet light, both from the sun and from the general interplanetary background, begins working on that frost. Methane molecules are broken apart and reassembled into heavier hydrocarbons, principally ethane. The lighter products evaporate away when the pole warms. The heavier ones cannot. They are far less volatile, and they stay. Over long stretches of time, those residues are irradiated further, into the class of reddish-brown organic solids that coat much of the outer solar system. The dark cap is, in the most literal sense available, Charon wearing Pluto's breath. The mechanism is elegant. It is also in trouble on the arithmetic. Producing a deposit that dark, that thick, and that extensive requires a great deal of processed methane, and when you combine the measured escape rate from Pluto's atmosphere with the fraction Charon can realistically capture, the supply comes up short. Models have to be pushed to the friendly end of every assumption to make it work at all. There are other gaps. The southern pole was in darkness during the flyby and was seen only faintly, lit by sunlight reflected off Pluto. We do not know whether it carries a matching cap. If it does not, the model has a serious problem, because there is no reason the process should favor one hemisphere. And nobody can say whether this is happening now, or whether Mordor is a relic, a deposit laid down in an era when Pluto's atmosphere was thicker and the supply was generous, sitting there ever since like a stain on a wall in an empty house. What makes this entry belong where it sits on the list is that no amount of studying Charon would ever have explained it. The answer is not on Charon. It is 400 kilometers away, in the upper atmosphere of a different world, and it took a spacecraft measuring the escape of gas from one body to account for the color of another. It is worth registering how unusual it is to have predicted any of this in advance. The cold trap idea was published before the flyby, as a prediction of what Charon's winter pole ought to look like if Pluto's atmosphere really was leaking. Very few pre-flyby predictions survived contact with the actual data. Most of what New Horizons found at Pluto was a surprise, and several confident models were retired within days of the first images arriving. The red pole was one of the rare cases where somebody said what would be there, and it was there. The escape of methane that feeds it was measured directly during the encounter by an ultraviolet spectrograph called ALICE, which watched the sun set through Pluto's atmosphere and read the composition off the absorption. Some scale is useful here too. Charon is about 1,212 kilometers across. That makes it larger than any object in the asteroid belt, larger than several of Saturn's mid-sized moons, and large enough that if it orbited the Sun independently, it would be counted as a dwarf planet without argument. This is not a small rock with a stain on it. It is a substantial world with a permanent feature the size of a country, produced by a process that has no other known example. Astronomers have looked for similar polar darkening on other moons that orbit close to bodies with escaping atmospheres and have not found it. Mordor Macula remains a sample of one. Charon has two more features worth carrying with us because both point the same direction. The first is a system of canyons. Serenity Chasma is part of a tectonic belt running roughly 1,800 kilometers across the surface, and in places it is 7.5 kilometers deep. For comparison, the Grand Canyon is about 450 kilometers long and a little under 2 kilometers deep at its deepest. Charon's canyon system is 4 times longer and several times deeper, on a body about 1/10 of Earth's diameter. The standard reading is that Charon once held a subsurface ocean of liquid water, and that the ocean froze. Water expands by about 9% when it freezes. An expanding interior pushes outward on a rigid crust until the crust fails, and when it fails in tension. It splits. Serenity Chasma is what that looks like from orbit. The second feature is Vulcan Planitia, the smooth plain covering much of Charon's southern hemisphere. It is conspicuously free of the cratering that marks the terrain to its north, which means it was resurfaced. Something flowed across it. On a world where the temperature never gets close to melting rock, the flowing material would have been water and ammonia slush erupting from below, cryovolcanism. Neither the timing of that resurfacing nor the source of the heat that drove it has been established. Ammonia turns up elsewhere on Charon as well, concentrated in bright patches around fresh craters. That detail is more useful than it sounds. Ammonia exposed at the surface is destroyed by radiation within a few tens of millions of years. Finding it means it was excavated recently from material stored below, and it means there is ammonia down there to excavate. Ammonia is an effective antifreeze. Mixed with water, it can stay liquid at temperatures well below the ordinary freezing point. So the picture that assembles itself is of a moon that used to be warm inside, that cracked its own crust when it cooled, that resurfaced parts of itself with erupted slush, and that has been slowly painting one of its poles with the atmosphere of the world it circles for as long as that atmosphere has been leaking. Which raises an obvious question about the atmosphere doing the painting. Pluto's air has been supplying Charon's North Pole for a very long time. According to every model anyone had before the flyby, it should not have been supplying anything at all by now. It should have frozen out and fallen to the ground decades ago. It has been doing the opposite. Number 17. The atmosphere that refused to collapse. Pluto has an atmosphere, and the way we found out is a good illustration of how thin the evidence gets at this distance. In 1988, Pluto passed in front of a star. If Pluto were a bare rock, the star's light would have cut off instantly, like a switch. Instead, it faded gradually over several seconds, because a layer of gas was bending and scattering the light before the solid surface arrived. That gradual fade is the entire discovery. The observation was made from an aircraft carrying a telescope, the Kuiper Airborne Observatory, named after the same man the belt is named after. The atmosphere is mostly nitrogen, with traces of methane and carbon monoxide. At the surface, it is about 100,000 times thinner than the air we are breathing. It is held there not by any great gravitational strength, but by the fact that there is very little heat available to drive it away. Pluto reached its closest approach to the Sun in 1989 at just under 30 astronomical units, and it has been moving away ever since. It will not come back for 248 years. The prediction that followed from this was simple, confident, and printed in a great many places. As Pluto recedes and cools, the nitrogen will freeze out of the air and settle onto the ground, and the atmosphere will collapse. Some models gave it a decade or two. It did the opposite. Occultation measurements taken from 1988 through to 2015 showed atmospheric pressure roughly tripling, while Pluto moved further from the Sun every single year. By the time New Horizons arrived, surface pressure was around 10 microbars and still rising. The explanation is thermal inertia, which is a technical way of saying that large, cold things respond slowly. The nitrogen ice on Pluto's surface did not stop absorbing heat when Pluto passed perihelion. It kept absorbing and kept sublimating for decades afterwards, in the same way that the hottest part of a summer afternoon comes well after noon. At the same time, Pluto's northern hemisphere was emerging into sunlight after an extremely long winter, exposing fresh reservoirs of ice to warmth for the first time in generations. The atmosphere has been running on a lag measured in decades, and only in August 2018 did an occultation finally show the pressure beginning to fall. That is the first sign the lag is closing. The collapse is still expected. It is simply arriving much later than anyone said. Then the flyby broke a second prediction, and this one more thoroughly. The upper atmosphere was expected to be around 100 Kelvin and to be escaping at a furious rate. The picture in circulation before 2015 was of Pluto trailing a long comet-like tail of nitrogen streaming away behind it, losing its atmosphere so quickly that the surface would be visibly eroded over geological time. The ALICE instrument measured the upper atmosphere at roughly 70 Kelvin. That is far colder. And the escape rate came in around 10,000 times lower than the standard models had predicted. Pluto is not evaporating. It is holding on to its air with a firmness nobody expected. Something is cooling that upper atmosphere far more efficiently than nitrogen and methane can manage on their own, and the leading candidate is visible in the images. As New Horizons passed Pluto and looked back toward the Sun, it photographed the atmosphere backlit. What it saw were haze layers, more than 20 of them, distinct, sharply defined, stacked one above another to altitudes beyond 200 kilometers. They are not a smooth gradient. They are discrete bands, and the spacing between them is remarkably regular. The current best explanation for the cold is that these haze particles, rather than the gas molecules, are doing most of the radiating. A solid particle can shed heat into space far more efficiently than a nitrogen molecule can, so an atmosphere loaded with fine particulate matter runs colder than a clean one. That was in nobody's model before the flyby, and it has since been applied to thinking about other thin atmospheres in the outer solar system. The particles themselves are almost certainly the same class of reddish organic solids we met on Charon's pole. They form high in the atmosphere as sunlight works on methane and then they settle. Pluto is continuously snowing an extremely fine organic soot onto its own surface, which is where the dark reddish equatorial band gets its color. What produces the layering has not been settled. The leading proposal is atmospheric gravity waves, the same phenomenon that produces evenly spaced bands of cloud downwind of a mountain range on Earth, where air flowing over terrain oscillates as it recovers. Pluto has mountains up to 3.5 kilometers high, and winds that blow westward against the direction of its rotation, driven by ice sublimating on one side of the world and condensing on the other. The mechanism is plausible. The trouble is that the observed spacing does not cleanly match what any single version of the model predicts, and after a decade of work, the layers remain a description rather than an explanation. It is worth sitting with the timescale here, because it is the thing that makes this entry genuinely unresolvable rather than merely unresolved. Pluto's year is 248 Earth years long. Its seasons are correspondingly long, and they are made more extreme by the fact that Pluto's axis is tilted by about 120 degrees, so that its poles receive far more dramatic swings of sunlight than any other world we study closely. A single Plutonian season runs for around 60 years. The entire scientific record of Pluto's atmosphere begins in 1988. That is not one season. It is a little over half of one. Everything we believe about how that atmosphere behaves over a full orbit is therefore an extrapolation from a fragment. We watched the pressure rise for 27 years, and we have watched it begin to fall for a handful more. And from that, we are attempting to describe a cycle 2.5 centuries long. If the atmosphere does something unexpected in the 200 years between now and the next perihelion, nobody will be there with a comparable instrument to notice. Carbon monoxide was detected from the ground in 2011, before the flyby confirmed it, and that detection came from a telescope on a mountain reading a signal a fraction of a percent deep. This is the level of evidence the entire subject rests on. The haze deserves one more note of scale. Measured by extent rather than by mass, Pluto's atmosphere reaches a substantial fraction of the way toward Charon. It is almost nothing in terms of substance and enormous in terms of volume, which is a combination that has no equivalent anywhere in the inner solar system. There is a final oddity that gets less attention than it deserves. Pluto's atmosphere has a temperature inversion near the surface. It gets warmer as you go up, for the first few kilometers, which is the reverse of the arrangement on Earth. The methane is responsible. It absorbs sunlight at altitude and heats the air above the ground, while the ground itself stays locked at the temperature of sublimating nitrogen. It means the coldest place in Pluto's atmosphere is the bottom of it. All of this nitrogen has to be coming from somewhere. An atmosphere that thin still represents an enormous quantity of gas, and it is being replenished continuously from a reservoir of ice on the surface. That reservoir is not distributed evenly. Almost all of it sits in one place, a single basin on one side of the world. And that basin does not have a single crater on it. Number 16. The plain with no craters. The bright heart-shaped region on Pluto is called Tombaugh Regio, after Clyde Tombaugh, who found the world in 1930 and who has a small quantity of his ashes aboard the spacecraft that photographed it. The western lobe of that heart is a plain of frozen nitrogen roughly 1,000 kilometers across. It is called Sputnik Planitia, after the first artificial satellite, following a convention on Pluto that assigns names of historic spacecraft and explorers. It sits 2 to 3 kilometers below the terrain surrounding it, and it is almost certainly an ancient impact basin that later filled with ice. The object that made it is estimated to have been around 200 kilometers across. When the first high-resolution images came down, the crater counters went to work. Crater density is the fundamental dating tool in planetary science. An old surface has been exposed to bombardment for a long time and is therefore heavily cratered. A young surface has not. You count, you compare against an estimated impact rate, and you get an age. They found none. Not a scarcity. None. Across an area comparable to Texas and Oklahoma combined, on a world that has sat in the same bombardment environment as everything else out there for 4.5 billion years, there is not a single identifiable impact crater. That puts a hard upper limit on the age of the surface of about 10 million years, and the more aggressive analyses push it below 500,000. The contrast is abrupt. Crater counts on the uplands immediately surrounding the plain give ages in the billions of years, so this is not an artifact of image resolution or lighting. The boundary is real, and it falls at the edge of the basin. In geological terms, the surface of Sputnik Planitia is being made right now. What is making it is visible in the pictures once you know to look. The plain is divided into polygonal cells, most of them between 10 and 40 kilometers across, separated by shallow troughs. The pattern is unmistakable to anyone who has watched a pot of thick soup approach a simmer, or looked closely at the surface of a lava lamp. Two independent teams reached the same conclusion and published in the same issue of the same journal in June 2016, one led by William McKinnon and one by Alex Trowbridge. This is solid-state convection. The nitrogen ice is warm enough at its base and weak enough throughout that it overturns. Warmer material rises in the center of each cell, spreads out, cools, and sinks along the boundaries, and the whole cycle takes somewhere between 500,000 and 1 million years to complete. The troughs are where the ice is going down. The reason nitrogen can do this, and water ice cannot, is a matter of material strength at temperature. Solid nitrogen at around 37 Kelvin is remarkably weak. It deforms under its own weight far more readily than water ice does at any temperature found in the outer solar system. A layer only a few kilometers deep is enough to sustain the motion. McKinnon's team modeled it using viscosity measurements made on solid nitrogen in laboratories decades earlier, for reasons that had nothing to do with planets. There are details on that surface that nobody has fully accounted for. Dark streaks run across parts of the plain, all aligned with each other, apparently blown by wind. Fields of shallow pits cover some cells and not others, probably formed by sublimation, but the pattern of where they appear and where they do not has no accepted explanation. Where 3 or more cells meet, the troughs form clean, X-shaped junctions, which is the signature of a mature convective system rather than a young one. And there are hills. Scattered along the cell boundaries are dark mounds, some of them several kilometers across, and they appear to be blocks of water ice bedrock. Water ice is denser than most things we compare it to, but it is less dense than solid nitrogen. So on Pluto, mountains float. Blocks of water ice crust have broken off the basin walls, drifted out onto the nitrogen, and been carried along by the convection until they jammed against a boundary and stopped. There are chains of them lined up along the troughs, like driftwood, collected at the edge of a slow river. Consider standing at one of those boundaries. The ground underfoot is nitrogen ice at 37 Kelvin, and at that temperature it is as hard as granite. You would have no sense that you were standing on frozen air. The trough is a shallow depression a few hundred meters wide, and it runs to the horizon in both directions, a seam in the world. Overhead, Charon hangs in a fixed position and does not move, and will not move, because Pluto keeps the same face turned toward it permanently. The sunlight is about 1,000 times fainter than on Earth, which is still roughly 200 times brighter than a full moon, so you could read by it. Nothing appears to be happening. There is no wind you could feel, no sound of any kind, and no visible motion anywhere in the landscape. The nearest thing to an event is the dark mountain stranded in the trough beside you, a block of water ice the size of a small range, which has been traveling across this plain for hundreds of thousands of years at a speed no eye could register. The entire surface you are standing on is a single, slow current, and it is going somewhere, and it will get there long after everything you know has ended. The plain does not sit in isolation either. Along its eastern margin, nitrogen ice is flowing down into the basin from the highlands above, and it is doing so in a form anyone who has looked at a photograph of an alpine glacier would recognize immediately. There are valleys with flow lines running along them. There are lateral deposits banked up against the valley walls. There are places where two flows have merged, and the line between them is still visible downstream. This is glaciation, in the ordinary sense of the word, driven by ice that is soft enough to creep under its own weight, except that the ice is nitrogen and the temperature is 37 Kelvin. At the western margin, the situation reverses. There, mountains rise up to 3.5 kilometers above the plain, and they cannot possibly be made of nitrogen. Nitrogen ice is far too weak to hold up that much relief. It would slump into a mound within a geologically trivial period. Those mountains have to be water ice, which at these temperatures behaves like rock and can support the load indefinitely. So the basin is rimmed on one side by water ice peaks acting as bedrock and fed on the other by rivers of frozen air, and the entire volatile inventory of the world is concentrated in the middle of it. The open problem is the heat. Convection requires a temperature difference across the layer, which means heat must be flowing up from below. Pluto's rocky core supplies some through the decay of radioactive elements, but it is a modest core in a small world, and the models that sustain convection for billions of years need either a thinner ice layer than the observations comfortably allow, or more internal heat than Pluto should have. Estimates of the layer's thickness span 3 to 10 kilometers, which is a wide enough range that the energy budget simply is not settled. Something is keeping this plane in motion, and we cannot yet account for it. West of the plain lies terrain that is stranger still and much less discussed. It is called the washboard and fluted terrain, and it consists of long parallel ridges, regularly spaced, covering an area of several hundred kilometers. Nothing else on Pluto looks like it, and nothing on any other world provides an obvious analog. The leading proposal is that these are deposits stranded by an ancient nitrogen glaciation, that the plain was once far larger, that it retreated, and that the ridges are what it left behind, in the way a retreating glacier on Earth leaves moraines. That is a reasonable story, and it has not been demonstrated. Beyond that, to the south, sit Wright Mons and Picard Mons, two enormous domes with central depressions. If they are what they appear to be, they are cryovolcanoes, structures built by water and ammonia slush erupting from the interior and freezing in place, and they would be among the largest such features known anywhere. Their flanks show very few craters, which again implies youth. So Pluto, a world so cold that its bedrock is frozen air, has the most geologically active landscape yet found beyond Neptune. It has been renewing that landscape continuously for the entire span of our species' existence, and for a great deal longer, and every mechanism proposed to explain it runs short of energy. A plain that size, filled to a depth of kilometers with ice, is also a very large amount of weight concentrated in one place. And weight concentrated in one place can do something to a world that is difficult to believe until you see the evidence for it. Number 15. The world that rolled over. Sputnik Planitia sits at roughly 18 degrees north latitude and 180 degrees longitude. The second of those numbers is the one that matters, and it took a while for anyone to notice how strange it was. Pluto and Charon are mutually locked. Each keeps the same face permanently turned toward the other, which means there is a line running through Pluto that always points at Charon, and an opposite point on the far side that always points away. That line is the tidal axis. 180 degrees longitude is the far end of it, the anti-Charon point, the place on Pluto that is as far from Charon as it is possible to get. Sputnik Planitia is sitting almost exactly on it. The odds of a basin landing that close to that particular line, purely by chance, are around 5%. That is a difficult number. It is low enough to demand an explanation, and high enough that a coincidence cannot be dismissed, which is precisely the sort of figure that generates a decade of papers. In November 2016, 2 of them appeared in the same issue of the same journal, one led by Francis Nimmo and one by James Keene. Both reached the same conclusion by different routes. It is not a coincidence, because Pluto moved. The mechanism has a name: true polar wander. It works like this. A rotating body is stable when its mass is distributed symmetrically about its spin axis. If a significant excess of mass develops somewhere on the surface, that symmetry is broken, and the body responds not by changing its spin axis in space, but by rotating its entire crust and mantle relative to that axis, until the excess mass ends up in the position that is energetically favorable. When a large tidal companion is present, that favorable position is on the tidal axis. In other words, the whole planet rolls over to put the heavy part where the tides want it. Earth has done this on a small scale over its history. Mars is thought to have done it on a large one, with the enormous Tharsis volcanic bulge reorienting the planet by nearly 20 degrees. Pluto appears to have done it by tens of degrees, dragging its entire geography to a new set of coordinates. Now, here is the complication that makes this entry belong where it sits. A basin is a hole. A hole is a deficit of mass, not an excess. And a mass deficit does not migrate to the tidal axis. It migrates 90 degrees away from it, to the position that a mass excess avoids. If Sputnik Planitia were simply a large depression, true polar wander would have moved it to precisely the opposite place from where we find it. For the observation to work, something has to be adding mass beneath that basin. The nitrogen ice filling it helps, but nowhere near enough. Nitrogen ice is not dense, and the fill is at most a few kilometers deep. Something heavier has to be down there. The explanation both teams converged on is this. The impact that excavated the basin also thinned Pluto's ice shell beneath it. Ice is less dense than the material underneath. If you remove a great thickness of ice from one region, whatever lies below will rise to fill the space, in the way that a ship rides higher when cargo is removed. And if what lies below is denser than ice, the result is a net excess of mass concentrated exactly where the basin is. The best candidate for material that can rise like that is liquid water. A subsurface ocean, bulging upward under the weakened crust, supplies the missing mass neatly and without requiring anything exotic. So the position of a plane on a map becomes an argument for an ocean, by way of a body rolling over. That is a long chain of inference, and it would be reasonable to be skeptical of it. Which is why the second paper matters. Keene's work approached the problem from a completely different direction. Reorienting a body of Pluto's size does not happen without consequences. As the crust shifts relative to the spin axis, the shape the body is trying to hold changes, and the crust has to accommodate that change by deforming. The pattern of deformation is predictable. You can calculate, for a given amount and direction of reorientation, exactly where the crust should be pulled apart, in what orientation the faults should run and where it should be left undisturbed. Pluto's observed fracture network matches that prediction well. The great fault systems, including Virgil Fossae and Sleipnir Fossa, run in the orientations the reorientation model requires, in the places it requires them. Two entirely independent observations, where the basin sits and how the cracks run, both point to a world that changed its orientation and left the record on its own surface. One of those fractures adds a further detail. Virgil Fossae shows reddish material spread along and around its floor, deposited from below rather than falling from above. The best interpretation is that ammonia-rich water erupted along the fault at some point and froze on the surface. Ammonia at the surface is destroyed by radiation on timescales of tens of millions of years, so if that identification is right, the eruption was geologically recent. It is one of the strongest hints that Pluto has been doing something internally in the relatively recent past. There is a broader tectonic point that runs alongside all of this. Pluto's surface shows extensional features almost exclusively. There are faults where the crust has been pulled apart, and there is very little evidence anywhere of the crust being pushed together. That asymmetry is informative on its own, independent of the reorientation argument. A body that is cooling and contracting develops compressional features, wrinkles, ridges, thrust faults, because the surface area available has to shrink to fit a smaller interior. Pluto shows the opposite. Its surface area has been increasing. Something inside has been expanding. Rock contracts as it cools. Water expands by about 9% when it freezes. On a world made largely of ice and rock, only one of those materials can produce global expansion, and it can only do it by freezing. There is a consequence of all this that is rarely mentioned and worth a moment. If Pluto reoriented by tens of degrees, then its ancient equator is not where its equator is now. The bands of terrain that were once tropical and the regions that once held the poles have been carried to new latitudes. Any record Pluto's surface holds of its early climate is therefore written in the wrong place on the modern globe, and reading it correctly requires knowing the rotation that has since been applied. Current estimates put the ice shell at roughly 200 kilometers thick over a rocky core about 1,700 kilometers across, which means the shell that did the moving is a thin skin on a large stone. What remains unresolved here is a set of questions that cannot be answered from 4.5 billion kilometers away. Nobody knows how far Pluto reoriented or how quickly. Nobody knows whether the ocean that supplied the mass anomaly is still liquid today or froze after doing its work. And nobody can entirely exclude the possibility that the 5% coincidence is simply a 5% coincidence with a persuasive story attached to it after the fact. That last possibility is uncomfortable, and it is taken seriously in the literature, because the alternative is a conclusion about the interior of a world drawn entirely from the position of a stain on its surface. The chain of reasoning keeps arriving at the same place. To explain the plane, you need the reorientation. To explain the reorientation, you need mass. To explain the mass, you need something dense and mobile underneath. The best candidate is an ocean. And if it is there, it is still there now. Number 14, the ocean nobody can see. The case for liquid water inside Pluto right now rests on 3 independent legs, and it is worth being precise about this. Not one of them is a direct detection. Nobody has seen this ocean, measured it, or sampled it. The argument is entirely circumstantial, and it is nonetheless strong enough that it has become the standard position in the field. The first leg is the one we have just walked through. The basin needs a positive mass anomaly beneath it to sit where it sits, and an upwelled ocean supplies one more, naturally, than any alternative anyone has proposed. The second leg is the tectonics. Pluto's surface is covered in features formed by being pulled apart, and almost entirely lacks features formed by being pushed together. That is a measurement of the world's history of volume. It has been getting larger. A body of rock and ice that cools over 4.5 billion years should shrink, because rock contracts as it cools, and because a liquid interior that freezes to ice would ordinarily be expected to settle. Except that water is the exception among common substances. It expands when it freezes by about 9%, which is why pipes burst in winter and why ice floats. A global ocean freezing progressively from the outside inward would push the overlying shell outward, and the shell, being rigid and brittle at these temperatures, would eventually fail in tension and crack. Pluto's surface is cracked in exactly that way, everywhere, at every scale. The third leg is negative evidence, which is often the most persuasive kind. Pluto shows no fossil bulge. Bodies rotate faster when they are young, before tidal interactions have slowed them, and a faster rotation produces a larger equatorial bulge. If a body freezes solid early in its history, that bulge gets locked into the rigid structure and stays there even after the rotation slows, like a dent that never comes out. Several moons in the solar system carry exactly such fossil bulges. Pluto does not. Its shape is consistent with a body that has been able to relax and adjust its figure over time, which requires a warm, deformable interior for most of its history. The problem has always been keeping such an ocean liquid. Pluto is small. Its rocky core is modest. Radiogenic heating, the warmth released by the slow decay of radioactive elements in the rock, should have run down long ago, and the standard calculations do not obviously deliver enough heat to keep water liquid under 200 kilometers of ice for 4.5 billion years. Two papers changed the picture, and they took opposite approaches to the same difficulty. In 2019, Shunichi Kamata and colleagues proposed adding an insulating layer. Specifically, a thin layer of gas clathrate hydrates at the base of the ice shell, cages of water ice with methane molecules trapped inside them, the same class of compound found in seafloor sediments on Earth. Clathrates are unusually poor conductors of heat. A layer only a few kilometers thick, sitting between the ocean and the shell above it, would act as a blanket. It would dramatically slow the rate at which the ocean loses heat upward, keeping it liquid for far longer, while simultaneously keeping the ice shell above it cold and rigid. That second effect is not incidental. Pluto's geology requires a rigid shell to support the observed relief and hold the fracture patterns. A single layer explains two awkward observations at once, which is the kind of economy that makes a model persuasive. In 2020, Carver Beerson, Francis Nimmo, and Alan Stern took the other route and proposed that Pluto never needed to warm up because it started warm. Their argument is about how quickly Pluto accreted. If a body assembles rapidly, the gravitational energy released as material falls together does not have time to radiate away, and the body melts itself. Under this model, Pluto began with an ocean and has been slowly freezing ever since, rather than freezing early and being reheated. The observational signature is different. A hot start predicts extensional tectonics from the very beginning of the record, while a cold start predicts an initial period of compression as the world contracted, followed by expansion later as an ocean formed and refroze. The oldest surfaces on Pluto appear to show extension from the beginning, which favors the hot start. Current estimates put the ocean at roughly 100 to 180 kilometers deep, beneath an ice shell of around 200 kilometers, and probably loaded with ammonia. Ammonia is an effective antifreeze. Mixed with water, it can remain liquid at temperatures far below the ordinary freezing point, which is another way of making the energy budget work. If those estimates are approximately right, Pluto holds more liquid water than all of Earth's surface oceans combined. That sentence deserves a moment. There is a body 4.5 billion kilometers from the Sun, on which the daytime temperature never rises above about 40 Kelvin, which may contain more liquid water than our own planet. And the same reasoning applied to its neighbors suggests it is not alone. Eris, Makemake, Haumea, and Quaoar are all plausible candidates by similar arguments. If that holds, then subsurface oceans are not a rarity in the solar system. They are one of the commonest environments in it, and every one of them is sealed beneath 100 kilometers or more of ice in permanent darkness, with no realistic prospect of anyone ever sampling one. None of this is confirmed, and the reason is a matter of instrumentation. There are two standard ways to detect a subsurface ocean. The first is to look for an induced magnetic field. A conducting salty layer moving through an external magnetic field generates a signature that can be measured from orbit, which is how the case for oceans inside Europa and Ganymede was made. That requires two things: a magnetometer on the spacecraft and an ambient field to induce against. New Horizons carried no magnetometer, and Pluto orbits far outside any planetary magnetic environment. The second method is to measure the body's tidal response, how much it flexes, which requires tracking it over time from orbit. That means an orbiter, and an orbiter means a mission that arrives and stays, rather than passing at 14 kilometers per second. There is no funded mission. There is no mission in development. The concepts that have been studied would take decades to arrive after launch, and no launch has been approved. Charon offers a preview of the alternative outcome. Its enormous canyon system is read as the record of an ocean that did freeze completely, splitting the crust as it expanded, the same process run all the way to the end on a smaller body with less heat available. It is worth remembering what the one visit actually consisted of. New Horizons came within 12,500 kilometers of Pluto and was past it in a matter of hours, traveling far too fast to stop. The data gathered during that encounter then took more than 15 months to reach Earth, transmitted at a rate slower than a domestic telephone modem from the 1990s. Everything argued above rests on that one pass. So the position is this. We have three independent lines of evidence, two competing models that both work, an estimate of the volume, and no way whatsoever to check. The question stays open until somebody goes back and stays, and nobody currently alive is likely to see it answered. That is one world, examined more closely than any other object beyond Neptune will be for a very long time. The rest of the belt has only ever been counted. And the count is missing something enormous. Number 13. The missing small objects. Everything smaller than about 10 kilometers across in the Kuiper Belt is invisible. That is not a limitation of any particular telescope. It is a limitation of all of them. An object that size, at 44 astronomical units, reflecting a few percent of a sunlight that is already 2,000 times fainter than it is here, produces a signal that does not rise above the noise of any instrument yet built. This is a serious problem, and it is worth being clear about why. The size distribution of a population, how many objects there are at each size, is the fingerprint of how that population formed. It is the single most diagnostic thing you can measure about a collection of small bodies. And the informative part of the distribution, the part where the different formation models diverge most sharply, is precisely the part we cannot see. There is one workaround, and it is elegant. Small Kuiper Belt objects hit large ones. When they do, they leave craters. Counting craters on Pluto, on Charon, and on Arakoth is therefore a census of the impactors, and the impactors are the small objects. We cannot see them, but we can count the holes they made. In 2019, Kelsey Singer and colleagues published that count, and it overturned an assumption that had stood for decades. Craters smaller than about 13 kilometers in diameter are strongly deficient. There are far fewer of them than there should be. Translating crater size back into impactor size, that means the population of Kuiper Belt objects below roughly 1 to 2 kilometers across drops away sharply. The small bodies are simply not there in the numbers expected. Unpacking why that matters takes a moment. Consider a population of objects that has been colliding for a very long time. Big objects break into medium ones. Medium ones break into small ones. Small ones break into dust. Run that process for billions of years, and the population settles into a characteristic mathematical relationship between size and number, worked out for asteroids by Jerzy Dohnányi in 1969 and confirmed many times since. It is a robust result. Any population that has been ground down collisionally looks like that. The Kuiper Belt does not look like that at the small end. The grinding either never happened or never got far. That single observation reframes the entire region. The belt is not a rubble field produced by 4.5 billion years of demolition. It is much closer to an original inventory. The objects out there are broadly the sizes they were made at, sitting where they were left. It is a fossil, not a battlefield. There is a reason the impacts were gentle enough to preserve that. Collision speeds in the Kuiper Belt are around 1 to 2 kilometers per second. In the asteroid belt, they are closer to 5, and in the inner solar system, higher still. Orbital velocities fall with distance from the Sun, so encounters out there happen at a fraction of the energy. Two objects meeting in the Kuiper Belt are not so much colliding as bumping. The crater result lines up with a formation model that has become dominant over the last 15 years, and which will keep appearing on this list. It is called the streaming instability, developed principally by Andrew Youden, Jeremy Goodman, and Anders Johansson, and since reproduced in high-resolution simulations many times over. The older picture of planet formation was hierarchical and violent. Dust sticks into pebbles. Pebbles collide and stick into boulders. Boulders build into kilometer-scale planetesimals. Planetesimals accumulate into planets. Every step requires objects to survive collisions that ought to shatter them, and the step from pebbles to kilometer bodies was always the weak point. At those sizes, collisions destroy more than they build. The streaming instability skips it. In a disk of gas, solid particles feel drag, while the gas does not orbit at quite the same speed. That mismatch causes pebbles to drift, and drifting pebbles concentrate each other, because a clump of pebbles slows the local gas and makes it easier for more pebbles to join. Beyond a certain density, the clump becomes self-gravitating and collapses directly into a solid body tens to hundreds of kilometers across. The intermediate sizes never exist. Objects are born large. That is exactly what a crater record deficient in small impactors would look like. The model predicts a characteristic birth size in the neighborhood of 100 kilometers, and the observed distribution of large Kuiper Belt objects shows a turnover in roughly the right place. Arakoth, which we will come to shortly, reinforces the same conclusion from a different direction. On a body 22 kilometers long, it carries essentially one significant crater, informally called Maryland, about 7 kilometers across. A body that has spent 4.5 billion years in a densely populated collisional environment should be saturated with craters. Arrokoth is nearly clean. The evidence is not unanimous, and this is where the entry becomes properly unresolved, rather than merely surprising. There is a second way to detect small objects, called occultation. You point a telescope at a star and watch for a momentary flicker as an unseen body passes in front of it. The dimming lasts a fraction of a second. Done at scale, across many stars for many hours, it can in principle count objects far too small to image directly. In 2009, an analysis of Hubble data by Hilke Schlichting reported the detection of an object roughly a kilometer across by this method. Japanese ground-based occultation work has claimed further detections. Dedicated survey projects have been constructed specifically to settle the question. They have not settled it. The occultation counts and the crater counts do not fully agree, and the discrepancy has not been reconciled. Occultation is a difficult technique in a way that is easy to underestimate. The signal is a brief dip in brightness, and it has to be distinguished from a bird, a satellite, a scintillation in the atmosphere, or a fluctuation in the detector. The false positive problem is severe, and different groups have made different choices about how aggressively to filter. So the most basic demographic fact about the largest structure in the solar system, how many things are in it, remains genuinely disputed. Two respectable methods disagree, and there is no third method available. Pluto and Charon do at least allow a cross-check against each other, because Charon has more ancient terrain exposed and therefore records a longer stretch of impact history. The two surfaces tell a consistent story, which is reassuring as far as it goes. It goes as far as two objects in one system. There is one further wrinkle in the crater method that has to be acknowledged, because it affects how much weight the result can carry. Converting a crater diameter into an impactor diameter requires knowing the impact speed, the density of both bodies, and the strength of the target material. Each of those is estimated rather than measured. Nitrogen ice, water ice, and rock all respond differently to the same impact, and Pluto's surface is a patchwork of all three. Singer's team handled this by counting on the oldest and most uniform terrains available, and by carrying the uncertainties through explicitly, which is the correct approach, and the deficit survives the full range of reasonable assumptions. But the result is a statement about a distribution inferred through a model, not a direct count of objects, and the people who work on it are careful to say so. The stakes attached to getting this right are larger than the subject sounds. If the belt is an original inventory, then the bodies out there are the closest thing the solar system has kept to a set of unaltered building materials, and every one of them is a sample of the disk that made the planets. If it is true, though, if the belt really was never ground down, then somewhere out there should be an object that was assembled gently and then left completely alone. There is one. A spacecraft has been to it. Number 12, the gentlest collision in the solar system. New Horizons launched in January 2006 with a target and nothing beyond it. The plan had always been to continue into the belt after Pluto. That was the entire scientific justification for going out there rather than somewhere closer, and it was written into the mission from the beginning. The difficulty was that there was no known object to go to. A spacecraft traveling at 14 kilometers per second cannot change direction meaningfully. The amount it can steer is set by the fuel remaining, and by 2014, that defined a narrow cone of reachable space, perhaps a couple of degrees across. Somewhere in that cone there had to be an object worth visiting. Nobody could find one. Ground-based surveys tried and failed. The problem was not the size of the search area, but the faintness of the targets and the background. The cone happened to point toward a region of sky crowded with stars near the galactic plane, which is close to the worst possible circumstance for detecting a faint moving object. In June 2014, with the spacecraft 8 years and 4.5 billion kilometers into a one-way journey and a year out from Pluto, Mark Buoy led a campaign to search the cone using the Hubble Space Telescope. That is not a small request. Hubble time is contested, allocated by committee, and awarded in hours. Buoy's team had to argue for enough of it to sweep a region of sky repeatedly, and then build a custom analysis pipeline to comb tens of thousands of images for something that moved by a few pixels between exposures. They found several candidates. One of them, catalogued as 2014 MU69, was reachable with fuel to spare. Sit with the shape of that for a moment. There was a spacecraft already most of the way across the solar system, on a trajectory that could not be undone, and the thing it was meant to visit after Pluto did not exist as far as anybody knew. It had to be found, in the dark, inside a cone of space defined by a fuel budget, before the window closed. They found it with months in hand. The object had been sitting there the whole time, unnumbered and unnamed, and the only reason it is now a place with a map is that a group of people declined to accept that the search had failed. On the 1st of January 2019, New Horizons passed 3,500 kilometers from it, at a distance of 6.5 billion kilometers from Earth. It remains the most distant object ever visited by anything humans have built. It is now called Arakoth, a Powhatan word meaning sky. What it turned out to be is the most important measurement the mission made, and it looks at first like nothing much. Arakoth is a contact binary. It is two separate bodies, touching. The larger lobe, informally called Wenu, is about 21 kilometers across. The smaller, Weo, is about 15. They meet at a narrow, brighter neck. The whole thing is dark red and shaped, from most angles, like a flattened snowman. Reconstructing the merger from the geometry gives a relative speed at the moment of contact of less than about 5 meters per second, and possibly as low as 2 or 3. That is walking pace. A person could have outrun it. At any meaningfully higher speed, the two bodies would have shattered instead of joining. There would be a debris field or a heavily deformed remnant, or nothing at all. Instead, the two lobes came together slowly enough that they simply stopped, and they have been stopped ever since. Two further details close the argument. Both lobes have identical color and identical spectra, which means they formed from the same material in the same place. This was not the capture of a passing stranger. And their rotation axes were aligned before they touched, which does not happen by chance. Aligned poles are the signature of a pair that spent a long time in a slowly decaying mutual orbit, circling each other and gradually spiraling inward. Arakoth is not the site of a collision. It is the end state of a binary that finally fell together. Picture the last hours of it. Two dark red bodies, each the size of a city, fill the sky for one another, turning slowly and in step. There is no atmosphere, so there is no sound and nothing to raise dust. The gap between them closes over hours at a speed slower than a walk. The surfaces meet. There is a slight flexing where they touch, some material compressing into the neck, and then nothing. Nothing shatters. Nothing scatters. No fragments spin away. The pair, now a single object, continues along the orbit it was already on, and it has held that orbit for 4.5 billion years without anything else happening to it at all. That is how the solar system's building blocks came together. Not by slamming, by drifting. All of which is powerful support for the streaming instability and a serious problem for the older, more violent picture of planet formation. But Arrokoth also delivered a puzzle nobody has solved. Both lobes are flattened. They are not spheres, and they are not the irregular potato shapes familiar from asteroids. They are lenticular, pancake-like, and the flattening is pronounced enough that it was the first thing anyone remarked on when the shape model was reconstructed. No formation model naturally produces that. Proposals include preferential sublimation of volatiles from the poles, which would flatten a body over time, and shaping during the collapse itself. Neither has been demonstrated, and the shape remains unexplained. The surface chemistry is also unresolved, and in a way that is harder to shrug off. Methanol ice was clearly detected, reported by Will Grundy and colleagues in 2020. Water ice was not clearly detected at all. Ammonia was absent. Water ice should be the dominant solid at that distance and that temperature. It is the default assumption for essentially every object out there. A body made almost entirely of ice, showing almost no signature of the commonest ice, is not something any model anticipated. It may be that a coating of organic material is hiding the water beneath. It may be something else. Nobody knows. Arrokoth is a cold, classical Kuiper Belt object, which means it almost certainly formed near where it now orbits and has never been scattered. Its surface temperature is around 30 to 40 Kelvin, cold enough that nothing has evaporated in the entire history of the solar system. It rotates once every 15.5 hours, and its rotation axis lies nearly in its orbital plane, so it rolls rather than spins upright. The flyby data took about 20 months to come back to Earth at a rate of 1 to 2 kilobits per second. The one thing on it that may have moved recently is the neck. The bright material there is thought to be fine particles that migrated down from the lobes under the object's own feeble gravity and collected in the low point between them. On a world where nothing else has happened since the solar system formed, dust rolling downhill counts as geology. The object also carries a small piece of naming history that says something about how recent all of this is. Before it was formally named, the mission team used the informal nickname Ultima Thule, drawn from classical geography, where it denoted the furthest place beyond the known world. The associations the phrase had acquired in the 20th century were raised after the flyby, and the informal name was dropped. Arrokoth, proposed with the consent of Powhatan representatives, was approved in late 2019. It is the most distant place we have ever been, and it was named less than 7 years ago. Which brings us to the color. Arrokoth is dark red, and so are a great many objects out there, and the redness is the only label those objects still carry from the place they were made. Nobody can read the label. Number 11. The red stuff. Keeper. Belt objects come in 2 colors. Not a range of colors, 2. Plot the measured surface colors of a few hundred of them, and they do not spread out along a continuum. They fall into 2 distinct clusters. There is a neutral to slightly gray group, and there is an intensely red group that astronomers call ultra-red. Between the 2 there is a gap, and very few objects sit in it. That gap has been one of the cleanest unexplained observations in the field for the better part of 3 decades. The redness itself is not the mystery. It comes from tholins, a term coined by Carl Sagan and Bishun Khare in 1979, for the class of complex organic solids produced when simple ices and gases are bombarded by ultraviolet light and cosmic rays over very long periods. They took the word from the Greek for muddy, after failing to find an existing term that fitted what they had made in the laboratory. Tholins are dark, sticky, chemically disorderly, and reddish-brown. Take methane, methanol, or ammonia. Leave it exposed to radiation for a few 100 million years, and you get them. The methanol detected on Arrokoth is precisely the sort of feedstock required. The mechanism is not in doubt. What is in doubt is why it produces two outcomes rather than a range of them. If reddening depended simply on how long a surface had been exposed, you would expect a smooth spread, slightly reddened objects, moderately reddened objects, heavily reddened objects, in whatever proportions their histories dictated. That is not what the data shows. The data shows two families with a valley between them, and any explanation has to account for the valley. The leading answer is that the split is not about exposure at all. It is compositional, and it is primordial. Somewhere in the young disk there was a boundary, an ice line, the distance beyond which a particular substance could condense as a solid rather than remaining a gas. The best candidates are the condensation points of methanol or ammonia, somewhere around 30 to 40 astronomical units. Objects that assembled beyond that line incorporated the feedstock that turns red under irradiation. Objects that assembled inside it did not, and stayed neutral no matter how long they were irradiated afterward. Under this reading, the two color groups are two birth populations. They formed in different parts of the disk, and Neptune's migration later stirred them together so that objects from both are now found on overlapping orbits. Color is the only surviving label of where an object was made. The bimodality is not a property of the object's histories since formation. It is a map of the disk, 4.5 billion years old, preserved in the one attribute we can measure from here. That picture became considerably sharper with the arrival of the James Webb Space Telescope. Beginning in 2023, survey programs led by Noemi Pinilla Alonso, Ana Carolina de Pra, and their colleagues obtained infrared spectra of dozens of objects beyond Neptune. Not just colors, which are crude, but actual spectra showing which molecules are present. They found 3 groups, not 2. The classifications were named after the shapes of the spectra themselves, the bowl type, the double dip type, and the cliff type. The bowl group is dominated by water ice. The double dip group shows carbon dioxide along with complex organics. The cliff group is rich in methanol and other carbon-bearing ices. These groups map onto the older color classes, but they are not identical to them, which means the underlying structure is a 3-zone disk rather than a 2-zone one. 3 chemical environments, 3 distances from the young sun, 3 populations that were later mixed. It is worth appreciating what changed to make that possible. Obtaining a usable spectrum of a distant Kuiper Belt object from the ground required entire nights on the largest telescopes available, and frequently produced data too noisy to classify with confidence. Webb can do it in minutes. The 3-class result exists because the observing time required dropped by a factor of 100, and a subject that had been arguing over a handful of spectra now had dozens. Measuring a color out there is itself harder than it sounds, and the difficulty explains why the bimodality took so long to establish. You cannot simply photograph the object once. You have to image it through several different filters, one after another, over a period of hours, collecting enough photons in each to get a reliable brightness. Meanwhile, the object is rotating, so its brightness is changing for reasons that have nothing to do with color, and you have to disentangle the two. Early surveys had error bars large enough to smear the two populations into what looked like a single broad distribution. The gap only emerged as sample sizes grew and the measurements tightened. For years, there was a genuine argument about whether the bimodality existed at all, and the argument was settled by patience rather than by any new idea. The comparison case that keeps the whole subject grounded is Titan. Saturn's largest moon has an atmosphere thick with orange haze, and that haze is tholin chemistry running continuously, at a scale and a proximity that allows detailed study. A probe has descended through it and sampled it on the way down. Titan is far warmer than anything in the Kuiper Belt, and its chemistry runs in a dense atmosphere rather than on a bare, frozen surface, so it is not a direct analogue. But it is the only place where this class of material can be examined in bulk, and much of what is assumed about the outer solar system's red surfaces is extrapolated from it. What is still not explained is more specific than it used to be, which is progress of a kind. Nobody has identified the actual molecules. No laboratory tholin analog reproduces the observed spectra exactly. We can make reddish organic residues in a vacuum chamber, and they look broadly right, and they do not match. The material responsible for the most conspicuous color in the outer solar system remains chemically unidentified, and the redness fades. Objects that migrate inward and become centaurs, bodies on unstable orbits between the giant planets, lose their ultra-red character. Something strips it, or covers it, or destroys it. The candidates are sublimation, removing the surface layer as the object warms, resurfacing by outgassing activity, throwing fresh material over the top, or thermal processing altering the chemistry directly. Nobody has established which. The reddest material in the solar system is also the most fragile, and we do not know what destroys it. There is a reason this matters beyond bookkeeping. The cold classical population, which we will come to, is almost uniformly ultra-red, and that uniformity is one of the strongest arguments that it never left its birthplace. Color is doing real work as evidence. Pluto's dark equatorial band is tholin-coated, and it is among the reddest large surfaces ever imaged in the outer solar system. And this same class of chemistry, delivered to the early Earth in cometary material, is a plausible feedstock for the processes that eventually produced life here. The muddy red substance nobody can identify is not a curiosity at the edge of the solar system. It may be the raw material we came from. Color is one thing an object can carry from the place it was made. It is faint, it is fading, and it is at least attached to the object itself. The next entry concerns something an object should not be able to hold on to at all. Number 10. The ring that should not survive. 50,000 Quaoar was found on the 4th of June, 2002 by Chad Trujillo and Michael Brown working at Palomar Observatory. It is about 1,100 kilometers across, roughly half the size of Pluto, and it has a small moon called Quaoar, found by Hubble in 2007. It is named for the creation force of the Tongva people, the indigenous inhabitants of the Los Angeles basin, where the Discovery Telescope sits. Quaoar is named for Quaoar's sun in the same tradition. For 20 years it was a fairly ordinary large Kuiper Belt object. It had a slightly high density for its class, implying a substantial rock fraction, and it showed crystalline water ice and ammonia hydrate on its surface, both of which are mildly interesting because radiation should destroy both within about 10 million years, meaning something is resurfacing it. That was the file. In February 2023, a team led by Bruno Morgado published a result that made it one of the strangest objects in the solar system. The technique was stellar occultation, the same method that found Pluto's atmosphere. You predict that an object will pass in front of a background star, as seen from a particular strip of the Earth's surface. You put telescopes along that strip. You watch the star. When the object passes, the star blinks out, and the duration of the blink at each telescope gives you a chord across the object's shadow. Assemble enough chords and you get a shape. Morgado's team had chords from a series of occultations recorded between 2018 and 2021, including one caught from space by the Cheops telescope. And in several of those records, the star did not only dim for Quaoar, it dipped briefly before and after, at a distance of about 4,100 kilometers from the center of the body. Galaxies will continue to drift. That distance is the problem, and to see why requires one piece of 19th century physics. In 1848, Edouard Roche worked out that there is a distance from a body inside which tidal forces overwhelm the self-gravity of any smaller object, so that loose material cannot clump together. Inside that limit, rings are stable and moons cannot form. Outside it, the reverse. Material collects itself into a moon and does so quickly. That boundary is called the Roche limit, and it appears in every introductory textbook as a hard rule. Quaoar's ring sits at roughly 7.5 times the body's own radius. The Roche limit for Quaoar is at about 1.8 thousand kilometers. The ring is at 4,100. It is not marginally outside. It is more than twice as far out as the boundary where rings are supposed to stop being possible. The standard calculation says ring particles at that distance around a body of Quaoar's mass should accrete into a moon on a timescale of decades. Not millions of years. Decades. So the ring should not exist, and if it somehow formed recently, it should already have finished turning into a small moon. A follow-up analysis later the same year, led by Christian Pereira, found a second ring, closer in at around 2,500 kilometers. So there are two of them, and the outer one is the one that violates the rule. Two explanations are on the table and neither is settled. The first is resonance. The outer ring sits very close to Quaoar's 1 to 3 spin-orbit resonance, the distance at which a particle orbits once for every 3 rotations of the body, and near a 6 to 1 resonance with Quaoar's orbit. Resonant forcing can, in principle, keep a population of particles permanently stirred up, repeatedly kicking their relative velocities high enough that when they collide, they shatter rather than stick. Accretion requires gentle collisions. Keep the collisions violent, and nothing ever accumulates. The second is material properties. If the ring particles are unusually elastic, highly porous, icy, extremely cold, then collisions between them could rebound rather than merge, regardless of where the particles sit relative to the Roche limit. Accretion depends on collisions being inelastic enough that kinetic energy is absorbed. Make the particles bouncy enough, and they will refuse to stick anywhere. Laboratory work on the mechanical properties of ice at 30 or 40 Kelvin is thin because there has not historically been much reason to do it. Nobody has demonstrated the required elasticity, and nobody has ruled it out. The wider point is that the Roche limit has been quietly demoted from a law to a guideline. It is still correct about what it actually describes, the balance of tidal and gravitational forces, but the assumption that material outside it will always accrete has turned out to be an assumption rather than a consequence. Quaoar is not alone in forcing this. In 2013, occultation observations revealed rings around Chariklo, a 250-kilometer body orbiting among the giant planets. That was the first ring system ever found around anything other than a giant planet, and it was entirely unexpected. Nobody had proposed that small bodies could have rings at all. In 2017, Haumea was found to have one. Now Quaoar has two. 3 small bodies with rings, all found by the same method, all around objects far too small for anyone to have predicted them. The technique deserves a note because it is the quiet hero of this entire subject. Predicting an occultation means calculating where a shadow, perhaps 1,000 kilometers wide, will fall on the surface of the Earth, months in advance, to within a few hundred kilometers, using an orbit derived from a handful of faint observations of an object nobody can resolve. Then you have to get telescopes to that strip of ground, and you have to hope for clear weather along it. For most of the history of the method, the majority of predicted events simply missed. What changed was Gaia, the European spacecraft that measured the positions of over 1 billion stars to extraordinary precision. Once the star positions were accurate, the predictions became accurate, and occultation went from a lottery to a working technique. There is a further consequence that is easy to miss. Every one of these rings was found by accident, in the sense that none of the occultation campaigns was designed to look for rings. They were designed to measure sizes and shapes, which is what occultation is normally used for. The rings turned up as unexplained secondary dips in the light curves, and in at least one case such dips had been recorded years earlier and set aside as instrumental noise. Nobody was looking, because nobody thought there was anything to look for. That raises an uncomfortable arithmetic. 3 ringed small bodies have been found among the small number of objects that have been occulted often enough and observed carefully enough for a ring to show up. The sample is not large. If 3 out of a few dozen well-observed bodies have rings, then rings around small, distant objects may be common rather than exceptional, and the outer solar system may contain hundreds of ring systems that nobody has any prospect of detecting. That would mean the standard picture, rings as a rarity confined to giant planets, has been wrong not by a detail, but by an order of magnitude. Quaoar's own surface adds one more open question to the file. Crystalline water ice and ammonia hydrate should both be destroyed by radiation in roughly 10 million years, and both are present. Something is refreshing that surface. Cryovolcanism has been proposed, which would mean a body 1,100 kilometers across, with no tidal heating from a large companion, is still internally active. There is no confirmation and no obvious energy source. Everything we know about Quaoar's rings comes from a handful of one-dimensional lines drawn through a shadow. Nobody has ever directly imaged any of these rings. We do not know their composition, their particle sizes, their thickness, or their color. We know they are there, we know how far out they are, and we know that according to the physics as it was understood, they should not be. A rule taught to every physics student as a boundary condition of nature turns out to have an exception 6.5 billion kilometers away, and we found it by watching a star blink. That is a rule broken quietly, by an object most people have never heard of. The next entry breaks one loudly, and the object is large enough that the damage is visible in its shape. Number 9. The fastest spinning world we know. Haumea is shaped like an egg that has been sat on. Its 3 axes measure roughly 2,100 by 1,680 by 1,074 kilometers. In its longest dimension, it is comparable to Pluto. In its shortest, it is half that. It is a large body, and it is emphatically not round, and the reason is that it is turning too fast to be round. Haumea completes a rotation every 3.92 hours. Nothing else larger than about 100 kilometers anywhere in the solar system turns that fast. To put that in context, Earth takes 24 hours. Jupiter, the fastest spinning planet, takes just under 10, and Jupiter is visibly flattened as a result. Its polar diameter is about 7% smaller than its equatorial one, which is obvious in any decent photograph. Haumea's long axis is nearly twice its short one. It is not flattened. It is stretched. The stretch is not a shape it inherited from anything. It is the equilibrium figure a self-gravitating body assumes when it rotates at that rate, the shape it settles into because rotation is fighting gravity hard enough to reshape the whole world. That in turn means Haumea has been spinning at approximately this rate for a very long time, long enough to relax into the configuration. This is not a recent event. At that rotation rate, the equator is close to the speed where material would simply leave. Haumea holds together because it is dense for a Kuiper Belt object, somewhere around 1,800 to 2,000 kilograms per cubic meter, which implies a substantial rocky interior beneath a comparatively thin shell of ice. A body of ordinary Kuiper Belt density spinning at 4 hours would be shedding material from its equator continuously. So something spun it up, and the natural candidate is a collision. Supporting that, Haumea sits at the center of the only confirmed collisional family in the Kuiper Belt. Roughly 10 objects share nearly pure water-ice spectra, unusually neutral colors, and orbits clustered around Haumea's own. They look exactly like what you would get if you stripped the ice mantle off a larger body and left the fragments traveling on similar paths. Haumea also has 2 moons, Hi'iaka and Namaka, both found in 2005, both spectrally consistent with the same event. The family members were identified by their unusual spectra first and their orbits second, and it is the combination of the two that makes the identification secure. Everything fits. And then the numbers arrive, and it stops fitting. The family's velocity dispersion, the spread of speeds implied by the range of orbits its members occupy, is only about 140 meters per second. That is far too low. A collision, energetic enough to strip a body's entire ice mantle and spin the remnant up to a 4-hour day, should scatter debris at speeds several times higher than that. The family we observe looks like the product of a far gentler event than the one required to explain Haumea itself. The two facts have refused to fit together since the family was identified in 2007, and the problem has not been solved. Alternative proposals exist. One is that the family did not come from Haumea directly, but from the later disruption of a large satellite that the original impact had already created, a 2-stage process in which the second stage is gentle and would naturally produce a low dispersion. Another is that proto-Haumea was already rotating close to instability before anything hit it, so that a comparatively modest graze was enough to tip it over the edge and shed a shell. Neither has been demonstrated to reproduce the full set of observations, and estimates of the family's age range from about 1 billion to 4 billion years, an uncertainty wide enough that it does not usefully constrain anything. In January 2017, an occultation added a ring. José Luis Ortiz and colleagues reported it at about 2,287 kilometers from the center, roughly 70 kilometers wide, sitting at the 3-to-1 spin-orbit resonance, the same kind of resonant position later found at Quaoar, which strengthens the case that resonances are doing the work in these systems. The ring had a practical consequence too. Earlier size estimates had attributed the ring's blocked light to the body itself, so finding it made Haumea smaller. And in 2019, a dark red spot was identified on the otherwise bright icy surface. Its composition is unknown. The surface itself is a further puzzle sitting on top of the others. Haumea is coated in almost pure crystalline water ice, which is unusual twice over. Pure water ice is rare out there. Most surfaces are mixtures dominated by darker, redder material. And crystalline ice is stranger still, because radiation should convert crystalline ice to amorphous ice, the disordered form, within a geologically short period. Finding crystalline ice means something is either resurfacing the body or annealing the ice back into order, and neither process has an accepted driver at Haumea's temperature. The same signature appears on the family members, which is part of what identifies them, and it presents the same problem on every one of them. The two moons add their own complications. Hi'iaka and Namaka orbit close to a 3-to-1 relationship with each other, and Namaka's orbit is being visibly perturbed. Its path changes measurably over the span of a few years, which is unusual enough to have required a dedicated modeling effort. Iaka, the larger of the two, is itself coated in what appears to be nearly pure water ice. There is a consequence of the fast rotation that is worth stating plainly, because it is difficult to picture. On a body stretched into that shape, the strength of gravity is not the same everywhere. At the tips of the long axis, a point is further from the center of mass and is also experiencing the greatest centrifugal effect from the rotation, so the effective gravity there is a fraction of what it is at the poles. If you could stand on Haumea, your weight would change noticeably depending on where you stood, and at the ends of the long axis you would weigh very little indeed. The horizon would also behave strangely, curving away sharply in one direction and gently in the other. Haumea takes about 284 years to orbit the Sun once. It has therefore moved through a little over 7% of its orbit since anyone knew it existed. Consider watching it turn. From a fixed point a few thousand kilometers away, Haumea does not look like a planet. It looks like something that has been pulled. The body is visibly an elongated ellipsoid, and it rotates end over end fast enough that the motion is apparent to the eye rather than requiring instruments and patience. A full rotation in under 4 hours, so the long axis swings past, then the short one, then the long one again, and the object's apparent size changes as it goes. The surface is almost pure water ice, and it is brilliantly white, reflecting a sunlight that is nonetheless faint enough to make the whole scene dim. Somewhere out in the plain, a thin, dark ring catches the light. 2 small moons move slowly against the stars. And the thing at the center of it is a world 2,000 kilometers long that is turning fast enough to have deformed itself, and has been doing so since before anything on Earth was alive. It is worth being explicit about how much of this rests on inference rather than observation. No spacecraft has been anywhere near Haumea. There is no image of it that shows a disk. The shape comes from the way its brightness rises and falls as it rotates, combined with occultation chords. The density comes from the shape combined with the mass, and the mass comes from the orbits of the moons. The ring comes from a secondary dip in one occultation light curve. Every number in this entry is a reconstruction, and the reconstruction has held up under scrutiny, but the object itself has never been seen as anything other than a point of light that varies. Haumea's discovery is the ugliest story in modern planetary astronomy, and it has never been resolved. Michael Brown's team at Palomar had observed the object in 2004 and were preparing to announce it. José Luis Ortiz's team at Sierra Nevada Observatory announced first, in July 2005. It later emerged that Ortiz's group had accessed the publicly available observation logs of Brown's telescope, which recorded exactly where Brown had been pointing and when. The dispute that followed was bitter and public, and it involved accusations that neither side has withdrawn. The International Astronomical Union eventually settled the credit in a way that satisfied nobody. It accepted the Sierra Nevada Observatory as the discovery site. It accepted Brown's proposed name, and it listed no discoverer at all. Haumea is the only major body in the solar system officially discovered by a place rather than a person. The name Brown proposed was that of the Hawaiian goddess of childbirth and fertility, with the moons named for her daughters, chosen partly because the telescope that found the moons stands on Mauna Kea. The name is a tribute. The credit line beneath it is a blank space, and it is permanent, and it is in the record for as long as the object has a name at all. There is something worth noticing in that. Every other obstacle on this list is distance, or darkness, or the limits of instruments. This one is people, and it is the only entry where the unresolved part will never be resolved by better data. Haumea was pulled out of shape by its own spin, and we can at least say that much with confidence. The next object was pulled out of shape by something nobody can point to, and the evidence for it comes entirely from watching a moon. Number 8. The world that is softer inside than it should be. Eris was recorded in images taken on the 21st of October, 2003, and identified in those images on the 5th of January 2005 by Michael Brown, Chad Trujillo, and David Rabinowitz. Before it had a formal name, the discovery team called it Xena. It is the object that ended Pluto's planetary status, and it did so by forcing a question nobody in the field wanted to answer. Early measurements suggested Eris was larger than Pluto. If Pluto is a planet, and this thing is bigger, then either this is the 10th planet, or there is something wrong with the definition. And behind Eris there was a queue: Quaoar, Sedna, Haumea, Makemake, all found within a few years of each other, all in the same size range. The question was not whether to add one planet. It was whether to add 10 or 50 or an indefinite number as the surveys improved. The International Astronomical Union met in Prague in 2006 and answered by removing Pluto rather than adding Eris. The resulting definition, requiring a body to have cleared the neighborhood around its orbit, is still argued about 2 decades later. The irony is that Eris turned out not to be larger. A stellar occultation on the 6th of November, 2010, observed from 3 sites in Chile, fixed its diameter at 2,326 kilometers. Pluto's, measured directly by New Horizons 5 years afterwards, is 2,377. Eris is slightly smaller. Several textbooks had already been printed on the other assumption. But it is about 27% more massive, which makes it substantially denser and therefore considerably rockier. Whatever Eris is made of, there is more stone in it and less ice than there is in Pluto. Its surface reflects about 96% of the light that falls on it. That is brighter than fresh snow, and it places Eris among the most reflective surfaces in the entire solar system. There is a reason, and the reason is seasonal. Eris is currently near aphelion, roughly 96 astronomical units from the Sun, on an orbit that takes 559 years to complete. At that distance, whatever atmosphere it can hold has frozen out completely and settled onto the ground as a uniform coating of nitrogen and methane frost. There are no old patches, no darkened regions, no accumulated tholin staining of the kind that covers Pluto's equator, because the entire surface has been repainted. When Eris returns toward perihelion, the frost will sublimate, and it will have a thin atmosphere again, but that is roughly 200 years away. So Eris is a world that erases itself once per orbit. Its methane ice shows a different spectral signature from Pluto's, indicating a colder surface with less atmospheric processing, which is consistent with a body that has spent the recent past in deep freeze. It is also worth noting how little of Eris's own history we have watched. It takes 559 years to go once around the Sun. Since its discovery in 2005, it has traversed under 4% of a single orbit. Every statement about its seasonal behavior, the frost cycle, the atmosphere that will return, the repainting of the surface, is a model rather than an observation, built from what we know of Pluto and scaled to a colder, more distant world. Nobody has ever seen Eris with an atmosphere. Nobody will for 2 centuries. The 2010 occultation deserves a note of its own, because it produced one of the most precise size measurements ever made of a distant body, and it was almost missed. The shadow was predicted to cross a narrow strip of South America. Cloud cover took out several of the planned stations. 3 sites in Chile recorded the event cleanly, and those 3 chords are the basis for the number that settled the Pluto comparison. Had the weather gone differently that night, the question of which object is larger would have stayed open for years longer, and the argument about planetary definitions would have proceeded without one of its central facts. The genuinely strange result arrived in 2024, and it concerns the inside of a body nobody has ever seen the outside of. Eris has a moon, Dysnomia, found in 2005 and named for Eris's daughter, the spirit of lawlessness. Michael Brown and Brian Butler analyzed its orbit in detail, and the analysis produced a conclusion about Eris's interior. The reasoning runs like this. Dysnomia is tidally locked to Eris, and its orbit is essentially circular. Getting a satellite system into that configuration requires dissipating a great deal of energy. Tidal interaction between 2 bodies converts orbital energy into heat by flexing them, and the rate at which that happens depends on how readily the bodies deform. A rigid body barely flexes and therefore barely dissipates. A deformable one flexes more and dissipates more. The amount of dissipation required to have circularized Dysnomia's orbit and locked its rotation in the time available is far more than a fully frozen, rigid Eris could have supplied. A solid ball of ice and rock does not flex enough. To make the numbers work, Eris has to have an interior that deforms, a convecting mixture of rock and ice rather than a frozen solid. In the phrasing that stuck, Eris is squishy. That is a conclusion about the deep interior of a body 4.5 billion kilometers further away than Pluto, drawn entirely from the shape of a moon's orbit. It is a remarkable piece of inference, and it is worth being clear about how thin it is. No spacecraft has ever been within billions of kilometers of Eris. There is no image of it that shows anything but a point of light. The method is new, the sample is small, and the same analysis applied to Pluto and Charon gives a consistent answer, which is reassuring but is not the same as verification. Eris's orbit is its own unresolved question, and it is the one that puts this entry where it sits on the list. The orbit ranges from 38 to 98 astronomical units and is inclined 44 degrees to the plane of the planets. 44 degrees is enormous. The planets orbit within a degree or 2 of a common plane because they formed from a flat disk, and Eris is a substantial body, the most massive known object out there, traveling on a path tilted almost halfway to vertical. It did not form there. Nothing that large forms on an orbit like that, because a flat disk does not produce tilted orbits. Eris was moved, and the only mechanism available with enough leverage is Neptune. During the era when Neptune was migrating outward through the disk, objects that came close to it were flung onto eccentric, inclined paths, and some of them ended up where Eris is. How a body of Eris's mass survived that process intact is not fully modeled. Scattering something that large requires a close encounter with Neptune, and close encounters with Neptune are usually terminal. Objects are either ejected from the solar system entirely or thrown inward. Eris was placed on a path that keeps it permanently beyond Neptune's reach without either destroying it or losing it. That is a narrow outcome, and Eris is not the only object that achieved it. The name was chosen deliberately. Eris is the Greek goddess of strife and discord, and Brown selected it for the argument the object caused. Dysnomia, her daughter, is the spirit of lawlessness, and Brown has acknowledged the name is also a quiet nod to the actress who played the character the object was informally named for. The object that redefined the word planet has never been seen as anything but a dot, and everything we claim to know about its inside comes from watching how its moon moves. Everything so far on this list has been a single object, or at most a single system. From here, the entries change. The next one is about a population, and the population is itself the argument. Number 7. The pairs that should have been torn apart. There is a population in the Kuiper Belt called the cold classicals, and the word cold has nothing to do with temperature. It refers to their orbits. They occupy a narrow band running roughly from 42 to 47 astronomical units. Their orbits are nearly circular and inclined by less than about 5 degrees to the plane of the planets. They are almost uniformly ultra-red. They are, as a group, small. And the evidence is now strong that they formed where they are and have never been anywhere else, which makes them the only population in the solar system for which that can be said. Everything else out there has been moved. The Plutinos were swept into resonance by Neptune's migration. The scattered disk was thrown outward by close encounters. Eris was flung onto a tilted orbit by something violent. The cold classicals were left alone, and the reason we can say so with confidence has nothing to do with modeling. It has to do with pairs. Roughly 30% of cold classical objects are binaries. That figure on its own would be remarkable. What makes it decisive is the kind of binary they are. These are wide pairs of nearly equal size and nearly identical color, separated by thousands of kilometers, orbiting each other slowly. Some of the separations exceed 100,000 kilometers, which is a substantial fraction of the distance from the Earth to the Moon, around bodies only a few hundred kilometers across. In the main asteroid belt, by comparison, the binary fraction is around 2%, and the companions are usually small chips knocked off a larger parent. 30% equal mass-wide binaries is not a variation on that. It is a different formation channel entirely. The fragility is the argument. A wide binary is held together very loosely. The two components are bound by their mutual gravity, and at those separations that binding is feeble. A single, moderately close pass by Neptune would unbind the pair permanently. So would a moderately energetic collision with a third body. So would almost any of the disruptive events that shaped the rest of the belt. These pairs are still there, in enormous numbers. That is not a statistical argument or a model output. It is a direct physical demonstration that the cold classical population has never been scattered, never been dynamically stirred, and never passed close enough to Neptune to matter. They are the untouched control group, and their survival is the evidence. It is worth dwelling on how strange the wide binaries are as physical objects, because the numbers do not communicate it well. Take two bodies, each perhaps 150 kilometers across, and separate them by 100,000 kilometers. From the surface of one, the other would appear as a small disk, roughly the size the Moon appears from Earth, but far dimmer, and it would take years to complete a single revolution. The two would be moving relative to each other at speeds measured in centimeters per second, slower than a person strolling, slower in many cases than a hand moves. They are less like a planet and a moon than like two objects drifting in the same current, held together by a gravitational bond so weak that a firm push would break it. And they have been drifting like that, undisturbed, for 4.5 billion years. Every planet in the solar system has been rearranged. The asteroid belt has been ground down and stirred repeatedly. The inner planets have been resurfaced by impacts, and at least one of them has been struck hard enough to produce a moon. Out at 45 astronomical units, in the same span of time, pairs of objects held together by almost nothing have simply continued to orbit each other, and the strongest thing that has happened to them is sunlight. How they formed is now reasonably well understood, and it points in the same direction as everything else on this list. When a cloud of pebbles collapses under the streaming instability, it carries angular momentum. It is rotating, because the disk it formed in was rotating. If it carries too much angular momentum, it cannot collapse to a single body. It collapses to two, which then orbit each other. Binaries are not a rare accident under this model. They are the natural and expected outcome whenever the collapsing clump is spinning fast enough, and the fraction of binaries produced in simulations is broadly in line with what is observed. There is a further test, and it has been passed. A 2019 analysis found that around 80% of cold classical binaries orbit in the prograde direction, the same direction as the solar system's overall rotation. Collapse models predict exactly that preference, because the collapsing clump inherits the disk's rotation. The older explanation, in which two independently formed bodies capture each other during a chance encounter, predicts no preference at all. Capture should produce prograde and retrograde pairs in equal numbers. The observed 80-20 split rules capture out. Arakoth belongs here. It is a cold classical, and it is understood as one of these binaries whose two components finally spiraled all the way in and touched. Everything about it, the identical composition of the two lobes, the aligned rotation axes, the walking pace contact, is the last chapter of the story this population tells. What is not settled is more specific than it used to be, which is generally the sign of a subject making progress. The true binary fraction is uncertain because wide pairs are far easier to detect than tight ones. A pair separated by 100,000 kilometers can be resolved by Hubble or by adaptive optics from the ground. A pair separated by a few hundred cannot be resolved by anything and would appear as a single object. The 30% figure is therefore a flaw rather than a measurement, and the real fraction could be substantially higher. There is also a disputed subgroup. In 2017, Wesley Fraser and colleagues identified what they called blue binaries, pairs with neutral rather than ultra-red colors, sitting in the cold classical region but not matching the population's defining characteristic. The proposal is that these are not native cold classicals at all, but objects that formed closer to the Sun and were pushed gently outward by Neptune and deposited there without being disrupted. If that is right, then the region contains two populations that look superficially alike, and some of the arguments built on the cold classicals as a pure sample need re-examining. Detecting any of this is at the edge of what is possible. The two components of a typical resolved binary are separated on the sky by a fraction of a second of arc, which is roughly the angle subtended by a coin at a distance of several kilometers. The objects themselves are near the faintness limit of the instruments used. Every one of these systems represents a substantial investment of time on a contested telescope. The cold classical population accounts for only a small fraction of the belt's total mass, despite occupying its most prominent band. Their low inclinations mean they can be searched for efficiently by sweeping along the ecliptic, which is why so many of the earliest discoveries after 1992 were cold classicals. They were the easiest things to find, and their apparent prominence in the early catalogues was partly a selection effect. If it is true that they never moved, then the way they are distributed in space is a direct measurement of the density of the protoplanetary disk at 45 astronomical units, 4.5 billion years ago. That is an extraordinary thing to have access to. It is a reading taken from the original material, in the original place, by looking at pairs of objects so loosely bound that a single close encounter would have ended them. They survived every event in the solar system's history, which is how we know that nothing much has happened there. And yet the belt they sit in is missing almost everything it was supposed to have. Number 6. The missing 99.9%. Add up every object we can see in the Kuiper Belt, Extrapolate sensibly for the ones we cannot, and the total mass of the region comes out somewhere around 1 to a few hundredths of an Earth mass. The commonly quoted figure is about 2%. 2% of an Earth is roughly a couple of moons. That is the entire contents of a structure larger than the whole region occupied by the planets, spread across a volume so great that if you were placed at a random point inside it, the nearest object of any size would typically be further away than the Earth is from the Sun. Now run the formation models. To grow bodies 100 kilometers and larger, in the numbers observed, in the time available before the disk of gas dispersed, the standard calculations require something between 10 and 30 Earth masses of solid material in that region. Not 2% of an Earth. 10 to 30 Earths. The belt is missing something on the order of 99.9% of the mass it should have been built from. This is one of the oldest problems in outer solar system science, and it has 3 families of answer. They are not variations on a theme. They are genuinely different accounts of what happened, and the field has not chosen between them. The first answer is that the mass was there and was removed. This is the territory of Neptune's migration and the models that grew out of it. Renu Malhotra showed in 1993 that Neptune must have moved outward, pushed by its interaction with the disk of material it was clearing, and that as it moved, its orbital resonances swept through the region ahead of it, capturing objects as they went. The prediction was that objects would be found concentrated in Neptune's 3:2 resonance, and they were, the Plutinos, about a quarter of everything known out there. Later and more elaborate reconstructions added a period of instability among the giant planets, during which the primordial disk was scattered violently. Most of the original material was thrown into the inner solar system, into the Sun, or out of the solar system entirely. What remains is residue. This explanation has a great deal going for it. It accounts naturally for the resonant populations, for the scattered disk, and for the general dynamical structure of the region. It also implies something worth pausing on. If 10 to 30 Earth masses really were ejected, then a very large number of 100-kilometer bodies that formed around our Sun are now drifting in interstellar space. The objects that have been detected passing through the inner solar system from outside, one in 2017, one in 2019, another in 2025, are precisely what other stars doing the same thing to their own outer disks would produce. We are seeing their ejector, and they, in principle, are receiving ours. There is a comparison available that makes the deficit feel less like an accounting error and more like a genuine anomaly. We can observe debris disks around other stars directly. They show up as an excess of infrared light, produced by dust warmed by the star, and in a growing number of cases, they have been imaged in scattered light as visible rings and belts. Those disks routinely contain far more mass than our Kuiper Belt does. Some of that difference is a selection effect. The disks we detect most easily are the massive ones, and they tend to be around young stars that have not yet had time to deplete. But the gap is large, and it is not obviously closed by those corrections. If our belt is genuinely at the low end, then either something unusual happened here, or something unusual is happening in the way we count. The second answer is that the mass was never there. If the streaming instability is efficient enough at converting pebbles directly into 100-kilometer bodies, then it does not need a massive disk to work through. The requirement for 10 to 30 Earth masses came out of the older hierarchical model, in which most material is wasted in collisions that destroy rather than build. Remove that inefficiency, and the mass budget collapses. Under this view, the belt is not depleted at all. It is simply what a modest outer disk produces when planetesimals form the efficient way, and the models demanding 30 Earth masses were built on the wrong physics. The third answer is collisional grinding, that the mass was ground into dust over billions of years and blown out of the solar system by radiation pressure. This one has been badly weakened by the crater evidence we came to at number 13. If small objects had been produced in quantity by grinding, they would have shown up in the crater record. They did not. So the argument is now essentially between the first two, and the cold classicals sharpen it into something uncomfortable. The scattering explanation requires enormous violence throughout the outer disk. The cold classicals, sitting at 42 to 47 astronomical units with their fragile binaries intact, are physical proof that at least one band of that region experienced no violence at all. Those pairs would not have survived it. That leaves three possibilities, all of which are actively defended in the literature. Either the scattering happened everywhere except in that narrow band, which requires an explanation of its own, or the belt is an assembly of two populations with completely different histories that now sit side by side, one native and undisturbed, the other implanted from elsewhere. Or the mass deficit has different causes in different parts of the region, and there is no single answer to give. It is worth being explicit about how the two leading answers could be told apart, because they are not equally untestable. Scattering and in-place formation predict different size distributions, different binary fractions, and different orbital structures. A population that was violently scattered should have lost most of its wide binaries and should show a distribution shaped by collisions. A population that formed efficiently and stayed put should retain its binaries and show the birth distribution more or less intact. Those are measurable differences. The obstacle is that measuring them requires exactly the small object census that nobody has been able to complete. Neptune's role in all this is worth stating precisely, because it is easy to overstate. Neptune is believed to have formed several astronomical units closer to the Sun than it now orbits, and to have migrated outward by interacting with the disk it was clearing, throwing objects inward and moving outward in reaction, in the same way a person stepping off a boat pushes the boat backward. That migration is well supported. What is disputed is not whether it happened, but how violent it was, how quickly it proceeded, and how much of the original disk it removed, as against how much was never there. There is also a more deflating possibility that deserves stating clearly. The total mass estimate rests on an extrapolation across exactly the size range we cannot observe. We count what we can see, we assume a size distribution, and we integrate. If the assumed distribution is wrong at the small end, and the disagreement between crater counts and occultation counts says that we do not know whether it is, then the total could be off by a large factor. The missing mass problem is partly a problem about missing data. One further complication: the mass estimate depends on how reflective the objects are. Brightness is what we measure. Size is what we want. Converting between the two requires an assumed albedo, and albedo has been directly measured for only a small number of objects. A population that is darker than assumed is a population of larger objects, and therefore more mass. And the classical belt is not the whole of it. The scattered disk, the objects on large eccentric orbits reaching well beyond it, may hold comparable mass or more, and it is far harder to survey, because its members spend most of their time too distant and too faint to detect. We find them near perihelion, and we assume the rest. There is one thing that can be said with some confidence, and it comes back to Arakoth. The belt assembled gently. Objects came together at walking pace and stayed together. A population built that way was never going to grind itself into dust, which means the missing 99.9% was not consumed from within. If it was ever there, something took it. And whatever did the taking left the plane of the solar system behind. Which is a problem, because some of the objects out there are not in the plane at all. Number 5. The objects going the wrong way. Everything in the solar system formed from a single flat rotating disk of gas and dust. That is the foundational fact of the field, and its most basic consequence is that everything ought to orbit in the same direction, in roughly the same plane. The planets do, to within a degree or two. The great majority of the Kuiper Belt does as well. Then there is 2008 KV42. It was found by the Canada-France Ecliptic Plane Survey, and it was nicknamed DRAC, after Dracula, because it appears to walk on walls. Its orbital inclination is 103.4 degrees. That number needs unpacking. An inclination of 0 means an object orbits in the plane of the planets, in the same direction. 90 degrees means it orbits perpendicular to that plane, over the poles. Anything above 90 means the orbit is retrograde. The object is going round the Sun backwards. DRAC is at 103. It is not merely tilted. It is past vertical, orbiting the Sun in the wrong direction, on a path nearly perpendicular to everything else. Its perihelion is around 20 astronomical units, and its aphelion around 71, so it spends its time crossing the outer solar system at an angle that nothing else takes. It is worth explaining why a retrograde orbit is so much harder to make than a merely tilted one, because the difference is not one of degree. Angular momentum is conserved. Every object in the disk started out with angular momentum pointing the same way, and gravitational scattering redistributes that momentum between bodies rather than destroying it. You can tilt an orbit by giving an object a push perpendicular to its motion, and repeated encounters can accumulate a substantial tilt. But to reverse the direction of travel entirely, you have to remove all of the original angular momentum and then supply an equal amount in the opposite sense. A planet on a near-circular orbit is not well equipped to do that. It can throw things outward, inward, and sideways with considerable force. Turning something around is a different operation. This is why the retrograde objects are treated differently from the merely inclined ones in the literature. A 40-degree inclination is a puzzle about efficiency. Can Neptune do it often enough? A 103-degree inclination is a puzzle about mechanism. Can Neptune do it at all? 2 corrections belong here, because this object is routinely misdescribed, and the misdescriptions are less interesting than the truth. The first is size. DRAC is roughly 50 kilometers across. It is sometimes described as 30 miles, which is around half that, and sometimes as an object capable of destroying the Earth. The second correction addresses that directly. DRAC never comes anywhere near Earth. Its closest approach to the Sun is 20 astronomical units, twice Neptune's distance from us, out beyond the orbit of Uranus. It does not cross the orbit of Saturn, let alone anything inside it. It presents no hazard of any kind, now or at any point in its future. The interesting thing about DRAC has nothing whatever to do with danger. It is that the object is going the wrong way, and it is not alone. In 2016, Ying-Tung Chen and colleagues reported an object designated 2011 KT-19, nicknamed Niku, from the Chinese for rebellious. Its inclination is about 110 degrees. Also retrograde, also close to perpendicular. And they noted something stranger than either object individually. Niku, DRAC, and several other high-inclination objects appear to share a common orbital plane. A handful of the most extreme orbits in the solar system are not randomly oriented with respect to each other. They are aligned. With the small numbers available, the statistical significance is not overwhelming, and it has been challenged, but it has not gone away either. Add 2015 BP 519, nicknamed Kaju, at an inclination of 54 degrees on a highly eccentric detached orbit, and there is a small population of objects that the standard picture does not produce. Neptune's scattering can lift inclinations. That is well established, and it accounts for a great deal of the belt's structure. But it struggles badly above about 40 degrees, and it cannot readily produce retrograde orbits at all. Throwing an object backwards requires taking away all of its original angular momentum, and then some, and a single planet on a near-circular orbit does not have a straightforward way to do that. The candidate explanations all involve something from outside the ordinary machinery. The first is capture from the Oort cloud. The Oort cloud, far beyond everything discussed here, is thought to be roughly spherical, with orbits randomized in every direction, so retrograde objects there are unremarkable. If bodies are occasionally injected inward from it, some would arrive on backward paths. Halley's Comet is retrograde for exactly this reason. The difficulty is explaining how an object gets from the Oort cloud onto a stable orbit with a perihelion at 20 astronomical units and stays there. The second is a close stellar passage tilting a subset of the disk early in the Sun's history. The third is the Kozai-Lidov mechanism, in which a distant massive perturber drives an object through slow cycles that trade inclination against eccentricity, pumping the inclination up while the perihelion rises, then reversing. This mechanism is real and well studied, and it requires something distant and massive to drive it. The fourth is capture of material from another star altogether, during the period when the Sun was still embedded in its birth cluster and passing stars were close enough to exchange material. The survey that found Drac deserves a word, because the manner of the discovery affects how much weight the object carries. The Canada-France Ecliptic Plane Survey was designed from the outset to characterize the orbital structure of the belt with fully understood detection biases. That is a specific and demanding methodology. The survey records not only what it found, but the exact probability that it would have found any given object it missed, as a function of that object's brightness, distance, and orbit. The point of building a survey that way is that its results can be used to make statements about the whole population, rather than only about the objects detected. When a survey of that design turns up an object on an orbit the models do not produce, the finding cannot be dismissed as a quirk of where somebody happened to point. There is a version of the same problem closer in, which suggests it is not confined to the outer solar system. A small body has been identified sharing Jupiter's orbit while traveling around the Sun in the opposite direction, a retrograde co-orbital held in a stable relationship with the largest planet in the system while moving against it. That object has its own literature and its own unresolved origin question, and nobody has established whether it is related to the population discussed here or is a separate accident. There is a further constraint that makes this urgent rather than merely curious, and it is the reason this entry sits this far down the list. Objects on orbits like Drax are dynamically unstable. They cross the paths of the giant planets at steep angles, and calculations give them lifetimes of a few 100 million years before they are ejected or absorbed. A few 100 million years is a long time by any human measure, and a short time in this context. It is around 1/20th of the age of the solar system. That means these objects cannot be primordial survivors that have been sitting quietly since formation. They have not been there long. They are being resupplied from somewhere, continuously, and the source population has not been identified. Something is still putting objects onto perpendicular and retrograde orbits in the outer solar system. Not 4 billion years ago. Now, on an ongoing basis, at a rate sufficient to maintain a detectable population against constant losses. There is a practical problem layered on top of the physical one. A perpendicular orbit takes an object entirely out of the plane where telescopes concentrate their searching. Nearly all surveys for distant objects have swept along the ecliptic, because that is where nearly everything is, and telescope time is scarce. A population that spends most of its time far above and below that band is almost certainly undercounted, possibly by a great deal. We may be seeing the small fraction of these objects that happen to be passing through the plane when somebody looks. That is beginning to change. The Vera Rubin Observatory surveys the whole visible sky repeatedly rather than concentrating on a strip, and it is expected to find objects on these orbits at rates no previous survey could approach. The solar system, in other words, is not finished settling. Something is still stirring its outer regions, and it is doing it now. And something has already put one object somewhere that nothing should have been able to reach. Number 4, the world nothing can reach. 90,377 Sedna was found on the 14th of November 2003 by Michael Brown, Chad Trujillo, and David Rabinowitz. It is roughly 1,000 kilometers across, and it is among the reddest large objects known anywhere. It is named for the Inuit goddess who lives at the bottom of the Arctic Ocean, a name chosen because the object was found in the coldest place then known. Its orbit is the entire point. Sedna's closest approach to the Sun is about 76 astronomical units. Its furthest is around 937. One orbit takes roughly 11,400 years. To see why that is a problem rather than merely a large number, you need two other figures. The first is Neptune's reach. Neptune's gravitational influence, the distance within which it can meaningfully alter an object's orbit over the age of the solar system, extends to somewhere around 45 or 50 astronomical units. Beyond that, its effect falls away to nothing useful. Sedna never comes closer than 76. Neptune has never touched it. Neptune could not have put it there. The second figure concerns the other end. The galactic tide, the collective gravitational pull of the Milky Way, and the passages of nearby stars can perturb objects whose orbits carry them many thousands of astronomical units out, into the region called the Oort cloud. Those forces are weak, but they act over enormous distances and enormous times, and they are entirely capable of lifting an object's perihelion away from the planets. Sedna's aphelion, at 937 astronomical units, is far too close for those forces to have done anything to it. Sedna sits in a gap between two mechanisms, touched by neither. It is too far out to have been placed by the planets, and too far in to have been placed by the galaxy. In the technical vocabulary, it is detached. Some sense of the scale involved is useful before going further, because the numbers in this entry stop meaning anything without it. Neptune orbits at 30 astronomical units. The Kuiper Belt's classical population runs out somewhere below 50. Sedna's closest approach is 76, which is already beyond everything discussed so far on this list. And that is the near end of its orbit. At the far end, it is 937 astronomical units out, which is more than 30 times Neptune's distance and roughly 20 times further than the belt's outer edge. Light from the Sun takes about 8 minutes to reach Earth, 4 hours to reach Neptune, and around 5.5 days to reach Sedna at aphelion. A radio command sent to a spacecraft there would take that long to arrive, and the same again to be acknowledged, so the round trip is a fortnight. Sedna spends the overwhelming majority of its 11,000-year orbit out in that region, moving slowly, and it is only detectable at all during the small fraction of its cycle near perihelion. Which raises an obvious and uncomfortable point, We found Sedna because we happened to be looking during the brief window when it is bright enough to find. There is no reason to think it is unusual. There may be an enormous population of similar objects out there right now, at the far ends of their orbits, entirely invisible, and the handful we know about may be nothing more than the few that happen to be nearby at the moment somebody built a survey. It is no longer alone, though the company is sparse. 2012 VP-113, found by Chad Trujillo and Scott Shepard and announced in 2014, has a perihelion of about 80 astronomical units. The discoverers nicknamed it Biden from the initials in its designation. Liliakuhonua, announced in 2018, has a perihelion around 65. Its name is Hawaiian and refers to the flight of the plover that yearns for land, chosen for an object on an enormously long journey. A small and slowly growing family of these objects now exists, and every one of them presents the same problem. The candidate explanations all involve something outside the solar system as it currently exists. The first is a stellar flyby. The Sun almost certainly formed in a cluster of hundreds or thousands of stars, and in a crowded cluster close passes are common. A star passing within a few hundred astronomical units, early on, would have perturbed the outer disk substantially, lifting the perihelia of a population of scattered objects and stranding them permanently out of reach of the planets. This explanation has the merit of accounting for both Sedna and, as we will see, the belt's outer edge. The second is capture. Rather than lifting our own objects, a passing star may have donated some of its own. Under this reading, Sedna did not form around the Sun at all. It formed around another star and was transferred during a close encounter 4.5 billion years ago and has been orbiting ours ever since. The third is an unseen planet, which is the next entry on this list. The fourth is the birth cluster in aggregate, not one dramatic encounter, but the summed gravitational noise of a dense environment acting over several million years before the cluster dispersed. Sedna reaches perihelion in the mid-2070s, around 2076. That is its closest approach to the Sun in 11,400 years. The last one occurred when the ice sheets were retreating from northern Europe and agriculture had not yet been invented anywhere. The next one after this will fall somewhere around the year 13,400. There is only one of these approaches that will happen while our species has telescopes and spacecraft, and it is this one. Mission concepts for a Sedna flyby have been studied on the strength of that window, using nuclear electric propulsion or solar sails, because a spacecraft launched today with conventional propulsion would take several decades to get there, even at perihelion. None has been funded. None is in development. Sedna's closest approach in 11,400 years falls within the lifetimes of people already born. It will not happen again until a date so distant that no institution, no language, and no country now existing is likely to survive to see it. Every civilization between now and then will look at the same catalog entry and see an object at 800 astronomical units and receding, and will know that the one moment it was reachable belonged to us, and that we did not build the spacecraft. The window is not closing slowly. On the timescale of a human institution, the 20 or 30 years it takes to design, fund, build and fly a mission to the outer solar system, it is already almost shut. Consider the view from there at the far end of the orbit. At 937 astronomical units, the Sun is a star. It is by far the brightest star in the sky, bright enough to cast a faint shadow, and it is unquestionably the dominant object up there. But it has no disk. At that distance, it is a point of light, like Sirius seen from Earth, only considerably brighter, and it gives no warmth at all. The surface temperature is around 12 Kelvin. Nothing sublimates. Nothing shifts. There is no weather and no erosion, and nothing that could be called an event. And the constellations are the same. 900 astronomical units is a great distance within the solar system, and it is nothing at all compared to the distances between stars, so the patterns overhead are the familiar ones, unchanged. The only difference between that sky and the one over Earth is that the Sun has joined the constellations. The reason the population matters more than any individual object is statistical. With 3 or 4 sednoids known, almost nothing can be said about the distribution of their orbits, and the distribution is where the answer lies. A population produced by a single stellar flyby would carry a particular signature. The orbits would share an orientation set by the geometry of that encounter. A population produced by capture from another star would look different again. A population shepherded by an unseen planet would show a clustering aligned with that planet's orbit. These are distinguishable outcomes, and distinguishing them requires perhaps dozens of objects rather than a handful. That is precisely what the Vera Rubin Observatory is expected to deliver. Its survey design, repeatedly imaging the entire visible sky to considerable depth over a decade, is close to ideal for finding slow-moving distant objects, and the number of known sednoids is expected to rise substantially. For the first time, the population's orbital distribution would be measured rather than guessed, and several of the explanations above would either survive that measurement or not. Sedna's surface never rises above about 35 Kelvin even at its closest. It has no known moon, which means there has never been a direct measurement of its mass. When it was announced in 2004, it was the most distant known object in the solar system, and the Discovery team described it at the time as the first Oort cloud object ever detected, which turned out to be not quite right in an interesting way. It is neither an Oort cloud object nor a Kuiper Belt object, and it required a new category. There is one more thing about the sednoids that has proved more consequential than any of them individually. In 2014, Trujillo and Shepard noticed that these objects, together with several other distant bodies, had suspiciously similar orbital orientations. They wrote it up as an observation and offered no strong explanation. 2 years later, somebody did. One of the explanations for Sedna is a planet nobody has ever seen. And that planet has a name, a predicted mass, and a predicted orbit. Number 3. The planet nobody has seen. On the 20th of January, 2016, Konstantin Batygin and Michael Brown published a paper in the Astronomical Journal arguing that the outer solar system contains an undiscovered planet. Their evidence was geometric rather than observational, and it is worth laying out carefully because the whole case rests on it. Take the most distant, most detached objects in the catalogue, those with perihelia beyond 30 astronomical units and semi-major axes beyond 250. There were 6 of them at the time. Look at the orientation of their orbits in space. An elliptical orbit has a long axis, and that axis points somewhere. It also sits in a plane, and that plane is tilted somehow relative to everything else. Those 6 orbits are clustered. Their long axes point in broadly the same direction, and their orbital planes are similarly aligned. They are not scattered randomly around the Sun. They are grouped. Batygin and Brown calculated the probability of that arrangement arising by chance at roughly 7 parts in 100,000. The reason this demands an explanation is that nothing known can produce it. Orbits at those distances are not coupled to anything in the accepted solar system. Neptune cannot reach them. The galactic tide is too weak at those distances to impose a preferred direction and would not produce this particular pattern in any case. And an alignment of this kind does not persist on its own. Orbits precess at different rates, depending on their exact parameters, so any clustering that was not being actively maintained would smear out over hundreds of millions of years. Something has to be holding them. The proposed shepherd is a planet of about 5 to 10 Earth masses, on an eccentric orbit with a semi-major axis somewhere between 400 and 800 astronomical units, inclined by perhaps 15 to 25 degrees, taking 10 to 20,000 years to complete a circuit. That would make it a small ice giant, or a large super-Earth, a category of planet that is extremely common around other stars and conspicuously absent from ours. It is worth saying what kind of planet this would be, because the answer is a little surprising. 5 to 10 Earth masses puts it in the range between Earth and Neptune, the super-Earth and mini-Neptune category. When astronomers began surveying other stars for planets in the 1990s and 2000s, that category turned out to be the single most common type of planet in the galaxy. It is present around a large fraction of the stars examined, and it is entirely absent from our solar system. We have 4 small rocky planets and 4 giants, with a conspicuous gap in the middle, where the most common kind of planet in the universe ought to be. If Planet 9 exists, that gap closes. Our system would have the standard planet after all, sitting far enough out that nobody noticed for 4 centuries of telescopic astronomy. That is not evidence for the hypothesis, but it does explain some of the appetite for it. The hypothesis earned serious attention for a reason that has nothing to do with the clustering it was built to explain. It explained other things it was not built for. It predicted a population of objects on nearly perpendicular orbits, thrown there by the same mechanism that maintains the alignment. Objects on nearly perpendicular orbits exist, Drac and Niku, from the previous entry, both of which were known but had no accepted origin. It offers a mechanism for detaching perihelia, which addresses Sedna and the other sednoids without requiring a stellar flyby 4.5 billion years ago. And it accounts for a small oddity that had sat unexplained for a long time. The Sun's rotation axis is tilted about 6 degrees relative to the plane of the planets. That is a modest number, and it had no good explanation. A massive body on an inclined distant orbit would, over the age of the solar system, torque the entire planetary system by roughly that amount. A hypothesis that explains the thing it was designed for is unremarkable. A hypothesis that explains 3 other things it was not designed for is why this one has occupied a decade of effort. It also had a precursor. Trujillo and Shepard had flagged the clustering of arguments of perihelion in 2014 when they announced 2012 VP 113. They noted the pattern and suggested a distant perturber might be responsible without proposing a specific object. Buttigieg and Brown's contribution was to run the dynamics properly and produce a concrete prediction. A word about how such a planet would have got there, since 5 Earth masses does not assemble itself at 400 astronomical units. The disk at that distance was far too thin to build anything substantial. So the standard account is that Planet 9 formed much closer in, among the giant planets, and was thrown outward during the period of instability that reorganized the outer solar system, flung onto a distant eccentric orbit by a close encounter with Jupiter or Saturn, and then had its perihelion lifted by the same passing stars or birth cluster environment that features in the Sedna explanations. It is, under this account, a planet that was very nearly ejected from the solar system altogether and stopped just short. There is an alternative version in which it was never ours at all, captured from a passing star during the cluster phase, in the same way Sedna might have been. That version has the advantage of not requiring a specific sequence of near misses and the disadvantage of being even harder to test. The search since has been extensive, and it has come up empty. Subaru's Hyper Supreme Cam, an enormous wide-field camera on an 8-meter telescope, has surveyed large areas of the predicted sky. Pan-STARRS and the Zwicky Transient Facility have been combed. The TESS archive, collected for an entirely different purpose, has been searched. Nothing has been found. The most important negative result is older and broader than any of these. In 2014, Kevin Luhman analyzed data from the WISE spacecraft, which surveyed the entire sky in the infrared. Infrared is the right wavelength. A cold, distant object reflects almost no sunlight, but does emit its own faint heat. Luhman ruled out any Saturn mass or larger body within 10,000 astronomical units, and any Jupiter mass body within 26,000. That does not exclude Planet 9, which at 5 to 10 Earth masses is far below those thresholds. But it decisively excludes anything large, and that matters a great deal for the entry that follows this one. The difficulty of the search is easy to underestimate. At 400 astronomical units, sunlight is roughly 160,000 times fainter than at Earth. An object reflects that faint light, and then the reflection has to travel back. A 5 Earth mass planet out there would be extraordinarily dim, and it would also be moving very slowly across the sky, a few arc-seconds per year at most. Slow motion is a problem, because the standard technique for finding solar system objects is to take images separated by hours or days and look for the thing that has shifted. Something that barely moves between images can be filtered out as a background star by the very software designed to find it. In 2025, a team led by Terry Fan reported a candidate that exploits exactly this. They compared 2 infrared surveys separated by 23 years, IRAS, which flew in 1983, and Akari, which flew in 2006, and looked for a source that had moved by the right amount in the right direction over that interval. They found a pair of sources that fit. It is unconfirmed. And if it is real, its implied orbit does not match the Batygin and Brown prediction well, which means it would be either a different object entirely or a sign that the prediction needs revising. It may also be noise. A single source in each of 2 old surveys is a thin thread. Batygin and Brown have published successive refinements since the original paper, narrowing the predicted mass and tightening the orbit as more distant objects have entered the catalogue. The current version of the prediction is more modest than the first, a somewhat smaller planet on a somewhat closer orbit, which is what a hypothesis being tested against data is supposed to look like. There is a historical shadow over all of this that the field is well aware of. The name Planet 9 is contested, and some researchers prefer Planet X, reviving Percival Lowell's term for the hypothetical body he spent years searching for. Lowell's Planet X was inferred from apparent irregularities in Neptune's orbit. Those irregularities turned out to be measurement errors. The planet did not exist. The search for it nonetheless turned up Pluto in 1930, entirely by accident, on a photographic plate examined by a 24-year-old Clyde Tombaugh. A planet several times the mass of Earth may be orbiting our Sun, and the question of whether it exists has been open for a decade for one reason: it is too dark to see. That is the case for the planet. The case against it is more interesting than simply pointing at an empty sky, because the strongest objection is not that we have failed to find something. It is that we may have looked at the sky strangely. Number 2. The answers that are not a planet. The Planet 9 hypothesis is a good hypothesis, and one of the marks of a good hypothesis is that it generates good opposition. This entry is the opposition, and it belongs on this list in its own right, because several of the alternatives are individually stranger than the planet they are meant to replace. The first and most damaging alternative is that the clustering is not real. Every survey that finds distant objects has biases built into it. It points where the weather is reliable. It avoids the galactic plane, where the density of background stars makes faint moving objects impossible to pick out. It observes at times of year determined by scheduling committees and by which part of the sky is up at night. None of that is negligence. It is how observational astronomy works. Now consider the consequence. An object is easiest to detect near perihelion when it is closest and brightest. If a survey looks at a particular patch of sky, it will preferentially find objects whose perihelia lie in that direction. Find enough objects that way, and their orbits will appear to point in similar directions, not because they do, but because you were looking that way. This is not a hand wave, and it is not an argument made by outsiders. It is the central finding of a major survey designed specifically to address it. The Outer Solar System Origins Survey ran on the Canada-France-Hawaii telescope and discovered over 800 objects beyond Neptune. Its defining feature was that its biases were fully characterized from the start. A characterized survey publishes not only what it found, but the exact probability that it would have detected any given object it missed, as a function of brightness, distance, and orbital geometry. That turns absence into evidence. You can state, with a number attached, how confident you are that a population is not there. Corey Shankman and colleagues in 2017 and Michelle Bannister and colleagues in 2018 reported that the distant objects found by that survey show no significant clustering once its biases are properly accounted for. A 2021 analysis by Kevin Napier and colleagues went further, combining the survey with two other well-characterized datasets, and reached the same conclusion. The alignment is not statistically significant. The counter-argument is that the combined sample of objects with the relevant orbital properties is still only around 20. At that size, adding or removing 2 or 3 objects changes the statistics materially, and both sides can produce a defensible number. This is what a genuine statistical dispute looks like when the sample is small and the stakes are high. The second alternative keeps the gravity and removes the planet. Anne-Marie Madigan and Michael McCourt proposed what is called an inclination instability. A population of distant objects, acting only through their own collective gravity, can spontaneously develop exactly the kind of orbital alignment that is observed. No external body is required. The objects organize each other. Antranik Sefilian and Jihad Tuma developed a related model in 2019, a massive but diffuse debris disk beyond Neptune, totaling perhaps 10 Earth masses spread across an enormous number of small bodies, would produce the same shepherding effect as a single planet of similar mass. Same result, no planet, and a mass distribution that would be far harder to detect than one object, because it is nowhere in particular. The third alternative is the one that gets the headlines, and it deserves to. In 2020, Jakob Scholz and James Unwin published a paper in Physical Review Letters asking, in essence, what if Planet 9 is a primordial black hole? A black hole of 5 Earth masses would have an event horizon about 5 centimeters across. 5 centimeters. It would be, for every practical purpose, invisible. It reflects no light, it emits negligible heat, and there is nothing out there for it to be actively consuming in a way that would announce it. It would do everything the planet does gravitationally, and nothing the planet does optically, which would account rather neatly for a decade of failed searches. Primordial black holes, if they exist, would not have formed from collapsed stars. They would have formed in the first fraction of a second after the Big Bang, from regions of the early universe dense enough to collapse directly. Whether any exist at all is an open question in cosmology. the proposed detection routes are indirect. One is to look for a halo of dark matter concentrated around it, annihilating and producing a faint point source of gamma rays. The other is microlensing, watching for the brief characteristic brightening of a background star as the object passes in front of it and bends the light. It is worth pausing on how good that idea is as a piece of reasoning, independent of whether it is true. A 5-centimeter object with the mass of 5 Earths is not an evasion of the problem. It is a precise answer to the specific question the searchers keep raising. Every failed survey has established that whatever is producing the alignment does not reflect sunlight the way a planet does. There are 2 ways to satisfy that constraint. Either the object is a planet and it is somewhere the surveys have not looked, or it is not the kind of thing that reflects light at all. The second option is stranger, and it is not less rigorous. The paper works out the observational consequences honestly and proposes ways to test them, which is what distinguishes a speculative hypothesis from a speculation. The fourth alternative is modified gravity, and the notable thing about it is who tested it. Michael Brown and Konstantin Batygin themselves examined, in 2023, whether the external field effect in MOND, a proposed modification to gravity intended to eliminate the need for dark matter, could produce the observed alignment. They found that it could, in principle, over billions of years. They did not advocate it, and it is not the favored explanation. But the authors of the Planet 9 hypothesis took the trouble to test a theory that would eliminate their own planet, and published the result. And the fifth belongs here for a different reason. It is dead, and understanding why it died is more useful than any of the live options. The Nemesis hypothesis was proposed independently in 1984 by Daniel Whitmire and Albert Jackson, and by Mark Davis, Piet Hutt, and Richard Muller. It held that the Sun has a distant dim companion, a red dwarf or brown dwarf, on a long orbit, and that its periodic approaches disturb the comet reservoir, sending showers of comets inward and causing mass extinctions on Earth. The trigger for the idea was a statistical analysis of the fossil record by David Raup and Jack Sepkoski, which appeared to show extinctions recurring on a 26 million year cycle. This was not a fringe proposal. It was published in serious journals by serious people, and it was taken seriously for years. It is now definitively refuted, and by exactly the measurement described in the previous entry. Lumen's analysis of the all-sky infrared survey excludes any object of Saturn's mass or larger out to 10,000 astronomical units, and anything Jupiter-sized out to 26,000. A companion star would have been far brighter in the infrared than either threshold. There is no companion star. There is no brown dwarf lurking in or beyond the Kuiper Belt. The idea, which still circulates widely, was tested by a spacecraft that looked at the entire sky at exactly the right wavelength, and it found nothing. The extinction periodicity that motivated it has itself been repeatedly challenged on statistical grounds and is no longer widely accepted. That null result is one of the most valuable measurements in this whole subject, and it is worth stating plainly why. It is not that nobody has found a companion star. It is that somebody looked properly, everywhere, at the wavelength where such an object would be brightest, and established that it is not there. That is a different kind of statement, and it is the kind that closes questions. The most interesting thing about this entire argument is not who turns out to be right. It is watching a science decide, in public and slowly, how to tell the difference between something being out there and us having looked at the sky in a peculiar way. Both sides agree the dispute will be settled by better data rather than by further argument over the data we have. And every one of these arguments, the planet, the disk, the black hole, the modified gravity, the dead companion star, is about something beyond the belt. The last entry on this list is about the belt's own edge, and about whether it exists at all. Number 1. The edge that should not be there. The classical Kuiper Belt has an outer boundary, and it is abrupt. Count objects as a function of distance from the Sun, and the numbers rise through the 40s in the way you would expect from a normal population. Then, at roughly 47 to 48 astronomical units, they fall off a cliff. Beyond that line, the classical population effectively stops. There are still objects further out. The scattered disk has members on large eccentric orbits that carry them well past it, but the ordinary, well-behaved, low-eccentricity population that dominates the belt simply ends. The feature was characterized around the turn of the century, in work by Brett Gladman, Michael Allen, Gary Bernstein, and Renu Malhotra, among others, and every survey since has confirmed it. It is called the Kuiper Cliff, and it is the single most important unexplained fact about the region. The reason it matters is comparative, and this is the part that is easy to miss. We can see debris disks around other stars. They show up as an excess of infrared emission, and in a growing number of cases, they have been imaged directly in scattered light, visible rings and belts of dust and rubble surrounding other suns. Those disks routinely extend to 100 astronomical units, 200, several hundred. Extended outer disks are the normal condition. Ours appears to stop at 47.5. If that is real, our solar system is unusual in a way nobody can account for. And every conclusion that has ever been drawn about planetary systems in general by studying this one closely would need re-examining, because the object being studied would not be typical. There are 4 candidate explanations, and none of them is established. The first is a stellar encounter. A star passing within a few hundred astronomical units, early in the Sun's history while it was still embedded in its birth cluster, would have stripped the outer disk and left a sharp truncation behind. This explanation has the considerable merit of also accounting for Sedna, one event, 2 problems solved. It has the corresponding difficulty that it requires a specific encounter at a specific distance, and there is no independent evidence for it. The second is a planet mass body that swept the region clear. The cliff sits close to Neptune's 2-to-1 resonance, at about 47.8 astronomical units, which is suggestive. Resonant sweeping during Neptune's migration is a real and well-understood mechanism. Whether it can produce an edge this sharp, rather than merely a thinning, is disputed. Objects do exist in that resonance. They have their own name, the Tutinos, so the cliff is a drop in the non-resonant population, rather than a complete boundary. The third is that the disk genuinely ended there, because of some condition in the protoplanetary disk that prevented planetesimals from forming any further out. That would be a satisfying answer if anybody could identify the condition. The fourth is that the cliff is not a cliff, and the objects beyond it are simply too small or too dark for any survey to have detected. That fourth possibility has stopped being a technicality. New Horizons carries an instrument called the Venetia Burney Student Dust Counter. It is named for the 11-year-old English schoolgirl who suggested the name Pluto in 1930, and it was built and is operated largely by students at the University of Colorado. It is the simplest instrument on the spacecraft. It is a thin film of a plastic that generates a small electrical signal when something strikes it hard enough to vaporize. It counts dust grains. As the spacecraft crossed the belt and then crossed the cliff, the dust flux was expected to fall away, because dust in the outer solar system is produced by collisions between objects, and past the cliff there are supposed to be very few objects to collide. It did not fall away. In February 2024, a team led by Alex Donner published measurements in the Astrophysical Journal letters showing dust flux out past 50 astronomical units, running higher than every model predicted and continuing to around 55. Not marginally higher. Higher than the models can accommodate without adding something to produce it. Dust past the cliff implies objects past the cliff. The result has to be handled carefully, and the people who published it say so. Dust in the outer solar system has more than one source. Collisions between belt objects produce it, which is the interpretation that matters here. But grains also arrive from interstellar space, drifting into the solar system from outside, and at these distances, that contribution is not negligible and has not been cleanly separated out. There is a third possibility as well, that the models of how dust is transported outward from the belt's denser regions are simply incomplete, so that grains produced closer in are reaching further out than expected. Any of these would account for elevated counts without requiring a hidden population of objects. What makes the measurement compelling despite all that is the size of the discrepancy and the fact that it does not decline where it was supposed to. A modest excess could be absorbed by adjusting the transport models. A flux that keeps running high across 5 astronomical units past the boundary is harder to absorb. There is also a limitation worth naming on the comparison with other stars. The debris disks we detect around other suns are found by their infrared excess, and the ones we can image are the brightest and most massive. Younger systems have more dust because their belts have had less time to be depleted. So the population of disks we can see is biased toward exactly the kind that would make ours look sparse. Correcting for that narrows the gap. It has not been shown to close it, and in any case the comparison that matters here is not about total mass, but about extent, where the disks stop sharply, and ours appears to be one of the very few for which we could even ask the question from the inside. There is a second thread, and it comes from the ground. Surveys conducted with the Subaru telescope in support of the New Horizons extended mission, searching, as Mark Buoy's Hubble campaign had a decade earlier, for a possible future flyby target, reported an unexpected concentration of objects at roughly 70 to 90 astronomical units. That is well beyond the cliff, in a region where the classical population is supposed to be absent. If that concentration is confirmed, the picture changes completely. The Kuiper Belt would not end at 48 astronomical units. There would be a belt, and then a gap, and then a second belt beyond it. And a gap and second belt structure is exactly what has been observed in several of the debris disks imaged around other stars, where it is normally attributed to a planet clearing the space between them. Our solar system would stop looking anomalous and start looking ordinary, and the cliff would be revealed as a feature inside the disk rather than the end of it. Consider what one of those measurements actually is. A grain of dust, perhaps a micrometer across, smaller than a red blood cell, smaller than most bacteria, is drifting somewhere past 50 astronomical units, where nothing has happened for a very long time. A spacecraft the size of a piano arrives traveling at 14 kilometers per second. The grain strikes a thin film of plastic on the outside of it and is vaporized instantly. The impact generates a charge pulse lasting a few millionths of a second. That pulse travels a short distance to an amplifier, becomes a number, and joins a cue in a memory that was designed in the 1990s. It waits there, sometimes for weeks, until the spacecraft turns and points its antenna back toward the sun. Then it is transmitted and it crosses 6 billion kilometers at the speed of light, taking about 7 hours to make the trip. It arrives at a dish in California, or Spain, or Australia, as a signal fainter than almost anything else humans deliberately listen for, and it is written down. One grain. One number. and the number is in the wrong place. This is where the list ends, and the honest answer is that we do not know. New Horizons is currently past 60 astronomical units and still working. It has enough power from its radioisotope generator to continue operating into roughly the 2040s, by which time it will be past 100. It is the only instrument that has ever been out there, and it is the only one that will be out there for decades. Neither Voyager carried a working dust detector at these distances, so its measurements are effectively unique. There is nothing to check them against, and nothing that could replace them. There is no confirmed future flyby target. The search continues, constrained as always by the narrow cone the remaining fuel allows. So the boundary of our own solar system, a fact printed in every textbook and drawn on every diagram, is currently being contradicted by a dust detector built by undergraduates, and nobody yet knows which is right. That is a fitting place for this list to finish, because it is where it began. Number 20 was an object that spent 23 years as a smudge, a handful of pixels with a catalog number, resolved into something genuinely strange only when a spacecraft happened to pass close enough to measure how fast it was turning. The Kuiper Cliff has been a line on a chart for a quarter of a century. It has been taught, cited, and used as a boundary condition in models. And it may turn out to have been a smudge as well, resolving now, as the counts come in, into something with a different shape. Everything on this list has the same character underneath. The belt is not a rubble field. It is a fossil, assembled gently, at walking pace, and left largely alone. What we have been looking at for 34 years is the original material of the solar system, sitting more or less where it was put, in the dark, at temperatures where nothing changes. Almost all of it is too small and too faint for us to see. The part we can see keeps turning out to be stranger than the models allow, objects spinning near the limit that would destroy them, moons that never settled, rings where rings cannot form, worlds that rolled over, pairs held together by almost nothing that have survived everything. And the frame we drew around all of it, at 47.5 astronomical units, appears to have been drawn in the wrong place. The edge of the solar system is being redrawn right now by a 20-year-old spacecraft carrying an instrument that a group of students built, 6 billion kilometers from anyone who could repair it. By the time it stops transmitting, sometime in the 2040s, the boundary in every textbook may simply have moved outward, and the belt we thought we had mapped will turn out to have been the near half of something larger. There is no hurry about any of it. It has been out there for 4.5 billion years, and it will still be there when the counting is finished. Sleep well, and good night.